So, here's something worth thinking about as you settle in tonight. Right now, as you're lying there, your body weighs something. Maybe 150 pounds, maybe 180, maybe more, maybe less. It doesn't matter. What matters is that all of that weight is pressing down into your mattress, and your mattress is pressing down into the bed frame, and the bed frame is pressing down into the floor, and the floor is pressing down into the foundation of whatever building you're in, and that foundation is pressing down into the earth beneath it. Your weight didn't disappear, it traveled. From your body, through every surface between you and the ground, all the way down until it reached something strong enough to absorb it completely. The earth, the bedrock, the thing that doesn't move. That journey, that invisible path your weight takes through every layer below you, that's the most important idea in all of engineering. And it's the key to understanding the most common, the most essential, and arguably the most beautiful structures that human beings have ever built. Bridges. There are more than 600,000 bridges in the United States alone. You probably drove over one today. You probably didn't think about it. And the reason you didn't think about it is that the bridge did exactly what it was supposed to do. It carried the weight of your car, and it sent that weight somewhere safe. And it did it so quietly and so reliably that you never had to wonder whether you'd make it to the other side. But here's the thing. Every one of those bridges is solving the same problem. A problem that sounds almost childishly simple when you say it out loud, but that has consumed some of the most brilliant minds in history for over 3,000 years. The problem is this. You've got a gap. Maybe it's a river, maybe it's a canyon, maybe it's a highway or a railroad track, and you need to get from one side to the other. You need something solid to stand on. Something that spans the empty space and holds you up. But there's nothing underneath that empty space. That's why it's a gap. There's no ground, no rock, no foundation to press down into. So the weight of the bridge and the weight of everything on it, all those cars and trucks and people, all that force pushing relentlessly downward, it has nowhere to go. And force always has to go somewhere. That's the rule. That's the one unbreakable rule of the physical universe. That every bridge must obey. You can't make force disappear. You can't cancel it out. You can't trick it or ignore it or wish it away. You can only move it. You can redirect it, channel it, split it into pieces, and send each piece along a different path. But at the end of every path, that force has to reach something solid enough to absorb it. If it doesn't, if the force has nowhere left to go, the bridge falls down. And so the entire history of bridge building, every arch and cable and tower and beam, every innovation and every catastrophe, every triumph and every tragedy, all of it comes down to one question. Where does the weight go? How do you take the downward pull of gravity on a bridge deck and reroute it, redirect it, make it travel sideways or upward or diagonally until it reaches solid ground? How do you build a road in the sky and convince the laws of physics to hold it there? And why does a stone arch that the Romans built 2,000 years ago still stand, while a modern steel bridge in Washington state ripped itself apart in less than 4 months? What did the Romans understand about force that 20th century American engineers somehow forgot? And here's the question that might keep you up for a few minutes before you drift off. Right now, somewhere near you, there is a bridge. And that bridge is holding weight. Cars, maybe. Trucks. The wind pushing against its side, its own weight.
thousands or maybe millions of pounds of concrete and steel, all of it pressing down, all of it obeying gravity, all of it asking the same question it's been asking since the day the bridge was built. Where do I go? And the bridge is answering. Right now, in the dark, while you're lying here, the bridge is answering. It's channeling force through cables, through arches, through beams and columns and piles driven deep into rock. It's taking every pound of weight and sending it on a journey that ends in the earth, every time, without exception, because there is nowhere else for it to end. That quiet, invisible, endless process of channeling force from the surface to the bedrock is the most fundamental act of engineering there is. Every skyscraper does it. Every dam does it. Every retaining wall and every foundation and every pile driven into the mud of a riverbed does it. But bridges do it in the most dramatic way possible. Because bridges do it over nothing, over air, over water, over the void. And the history of how people learned to do this, how they went from dropping a log across a creek to stringing cables between towers taller than skyscrapers and floating a highway half a mile above a canyon floor. That history is one of the great stories of human ingenuity. It's a story of mathematics and materials, of trial and error, and sometimes catastrophe, of engineers who built things that stood for millennia, and engineers who built things that collapsed in months. And every failure taught something. Every collapse was a lesson. And every bridge that stands today stands on the accumulated knowledge of every bridge that fell. Tonight, I want to take you on that journey. I want to trace the path that force takes through a bridge, from the surface where you drive to the bedrock far below. And I want to show you how over 3,000 years, human beings figured out more and more elegant, more and more daring ways to make that path work. We'll start with the simplest bridge imaginable, a log across a stream, and we'll end with a bridge deck floating half a mile above the floor of a Chinese canyon, held up by nothing but cables and the sheer stubbornness of good engineering. And along the way, I think you'll start to see something beautiful. That every bridge ever built, no matter how massive or how modest, is just a different answer to the same simple question. Where does the weight go? We'll go slowly. There's no rush. The bridges aren't going anywhere. They'll be standing in the morning, and the morning after that, and for years and decades, and sometimes centuries beyond. They were built by people who thought about the future, who designed for loads they'd never see, and storms they'd never witness, and earthquakes they'd never feel. They were built to last, and they do. Let's find out. Let's start at the very beginning. And I mean the very beginning. Long before engineering, long before mathematics, long before anyone had a word for force or compression or tension. Let's start with a river and a fallen tree. Somewhere, thousands of years ago, a tree fell across a stream. Maybe a storm knocked it down. Maybe the bank eroded beneath its roots. It doesn't matter. What matters is that someone, some early human being, looked at that tree and realized they could walk across it. They could get to the other side without getting wet, without wading through the current, without going around. That fallen tree is the first bridge. And even though nobody at the time understood why it worked, it was already solving the fundamental problem. It was taking the weight of a person and moving it sideways through the wood of the trunk until it reached the banks on either side. The banks were solid ground. They could absorb the force, and so the person made it across. Now this is worth pausing on for a moment because it reveals something important about how force behaves in a bridge. When you stand in the middle of a log that spans a stream, your weight pushes straight down. Gravity is pulling you toward the center of the earth, and it doesn't care that there's no ground beneath you. It just pulls. But the log doesn't let you fall. The wood is stiff enough to resist your weight, to hold its shape even with you standing on it. And here's what's happening inside that log as it holds you up. The top of the log, the surface you're standing on, is being squeezed together, compressed. Your weight is pushing down, and the fibers on top are bunching up, pressing against each other. Meanwhile, the bottom of the log, the underside, is being pulled apart, stretched. The fibers down there are in tension, being tugged away from each other as the log tries to bend under your weight. Compression on top, tension on the bottom. These are the two fundamental forces in almost every bridge that has ever been built. And they're happening right now, in every beam, on every overpass you've ever driven across. The top of the beam is being squeezed, the bottom of the beam is being stretched, and the weight is traveling sideways through the beam until it reaches the supports at either end, where it pushes down into the ground. That's a beam bridge, the simplest possible bridge design. And it's the design that accounts for the vast majority of bridges in the world today. Most bridges you encounter, the highway overpasses, the small creek crossings, the spans that carry roads over other roads, they're just sophisticated versions of that fallen log. A horizontal surface supported at both ends, with force traveling through it by compression and tension. But here's the problem with a beam bridge, and it's a problem that engineers have been fighting for 3,000 years. A beam bridge has a limit, and that limit isn't about how strong the material is. It's about something much more fundamental, something that Galileo Galilei figured out in the 1600s while he was under house arrest, of all things. Galileo asked a question that sounds so simple you'd think someone would have answered it centuries earlier. He asked, "Why can't you just make things bigger? Why can't you take a beam that works perfectly at 10 feet and just scale it up to 100 feet? And the answer, which he published in 1638 in a book called Two New Sciences, is one of the most important insights in all of engineering. When you scale something up, its weight increases faster than its strength. Let me explain what that means, because it's the reason every type of bridge beyond the simple beam had to be invented. Imagine you have a wooden beam that's 1 foot long, 1 inch wide, and 1 inch deep. It weighs a certain amount, and it can hold a certain amount of weight. Now double every dimension. Make it 2 feet long, 2 inches wide, 2 inches deep. How much heavier did it get? Well, weight depends on volume, and volume is length times width times height. You doubled all three, so the volume went up by 2 times 2 times 2, 8 times heavier. But how much stronger did it get? Strength in bending depends on the cross-sectional area, on how much material is there to resist the squeezing and stretching. You doubled the width and the height, so the cross-section went up by 2 times 2, 4 times stronger. So your beam is 8 times heavier, but only 4 times stronger. it got worse. It's carrying a larger fraction of its capacity, just holding itself up. And if you keep scaling, the problem keeps getting worse. Triple every dimension, and the beam is 27 times heavier, but only 9 times stronger. Eventually, if you make a beam long enough, it will collapse under its own weight before you put anything on it. This is called the square-cube law. And it's the reason you can't have an ant the size of a dog, because its legs would snap. It's the reason elephants have proportionally much thicker legs than mice. And it's the reason that simple beam bridges max out at relatively short spans. Modern bridge engineers use a rough guideline for this. The depth of a simple beam, the height of the steel or concrete section that carries the load, needs to be about 5% of the span length. So a 100-foot span needs a beam that's about 5 feet deep. That doesn't sound too bad. But a 500-foot span would need a beam 25 feet deep, which would be enormously heavy, and the weight of the beam itself would eat up most of its load-carrying capacity, leaving very little for the trucks and cars it's supposed to hold.
There's one clever trick that engineers use to get more out of a beam bridge, and it's worth understanding because it shows up in almost every modern highway overpass you'll ever cross. Instead of making each span work by itself, as a simple independent beam resting on piers at each end, you can make the spans continuous. You can run the beam all the way across multiple piers without a break, so that the spans are connected to each other. When you do this, something interesting happens. The spans help each other. A load on one span creates a reaction in the adjacent spans that actually stiffens the whole system. The result is that a continuous beam can be thinner than a simple beam spanning the same distance. That 100-foot span that needed a 5-foot deep beam as a simple span might only need a 3.5-foot beam if it's part of a continuous system. There's a trade-off, though. In a simple beam, the compression is always on top and the tension is always on the bottom. But in a continuous beam, the pattern flips over the piers. Right above each pier, the beam is being bent upward by the adjacent spans, so the top is in tension and the bottom is in compression. This reversal means the beam has to be designed to handle both conditions, which adds some complexity. And there's a detail that you can actually observe on highway bridges, if you know what to look for. In a continuous beam bridge, the steel beams often have splice points, places where two sections of beam are bolted or welded together. And those splice points are always located at specific positions along the span, offset from the piers by a specific distance. Why? Because at those particular points, the beam transitions from top in compression to top in tension. At the transition point, there's no bending force at all. Engineers call this the point of contraflexure. And because there's no bending force there, the splice can be smaller and simpler than it would need to be anywhere else.
So the next time you drive under an overpass and see a line of bolts partway along a steel beam, you're looking at a point of contraflexure, a place where compression and tension cancel each other out. And the engineers took advantage of the calm spot to join two pieces of steel together. There's a related detail that you can actually feel if you pay attention the next time you cross a bridge. Many bridges, especially older ones with precast concrete beams, have a slight bounce to them. You can feel your car rise and fall rhythmically as you cross. Each bounce corresponds to a span, the beam between two piers deflecting slightly under your weight and then springing back as you pass. This deflection is entirely normal and entirely intentional. Engineers design bridges to allow a small, controlled amount of flex. For a vehicular bridge, the maximum allowed deflection
is typically the span length divided by 800. So a 150-foot span can deflect about 2¼ inches under a truckload. You'd barely notice that as a driver. Maybe a slight softness in the ride, a subtle bounce. But it's there, and it's by design. The bridge is flexing, absorbing energy, channeling force, and springing back. Pedestrian bridges, interestingly, have stricter deflection limits. The rule there is span length divided by 1,000, which for the same 150-foot span allows only about 1¾ inches. The reason is comfort. Pedestrians are more sensitive to movement than drivers. They can feel vibrations through their feet, and excessive bounce makes people nervous. So the engineer designs the pedestrian bridge to be stiffer, not because it needs to be stronger, but because it needs to feel more stable to the people walking on it. But even continuous beams have limits. They can span a few hundred feet at most. And as the Industrial Revolution gathered speed, as railways spread across continents and cities grew into sprawling metropolises, a few hundred feet was no longer enough. For most of human history, this put a hard ceiling on how far a bridge could reach. If you were building with wood, you might span 30 or 40 feet. With stone, maybe a bit more if you used very thick, very heavy slabs. But to cross a wide river, a deep canyon, a broad valley, a beam just couldn't do it. The weight of the beam itself would crush it before it got anywhere close to the other side. And so, for thousands of years, people who needed to cross wide gaps had to get creative. In the foothills of the Himalayas, communities built rope bridges from woven vines, braided together and strung between trees on either bank. These bridges swayed and bounced, terrifying to anyone not used to them, but they worked because they were light enough that the square-cube law didn't destroy them. The ropes were in tension, pulled taut by the weight of whoever was crossing. And that tension travelled along the rope to the trees on either side, which were anchored in the earth. But rope bridges couldn't carry much weight. A single person, maybe. A loaded pack animal, probably not. A cart? Absolutely not. In the state of Meghalaya, in northeast India, on the border with Bangladesh, communities came up with something even more extraordinary. For almost 500 years, they've been building bridges out of living tree roots. The Ficus elastica, a species of rubber fig tree, sends out long aerial roots that can be trained across streams, woven together, and encouraged to grow into the opposite bank. Over decades, these roots thicken and strengthen, wrapping around each other, gripping the rocks of the streambed, forming a living structure that can carry 100 people at once. There's one particular bridge in Meghalaya that exists nowhere else in the world. A double-decker root bridge. 2 levels of woven roots stacked on top of each other, spanning about 65 feet across a jungle stream. And here's what makes these living bridges truly remarkable. They are the only bridges on Earth that actually get stronger with age. Every other bridge, every bridge made of stone or wood or steel or concrete, begins to degrade the moment it's finished. But a living root bridge keeps growing. Its roots keep thickening. Its connections to the earth keep deepening. A root bridge that's 50 years old is stronger than one that's 10 years old. A root bridge that's 100 years old is stronger still. These living bridges are a beautiful example of what engineers call bioengineering, the use of natural organisms as structural elements. And they show that human beings have been thinking about the problem of bridging gaps for a very, very long time. But root bridges take decades to grow,
Rope bridges sway and strain, and simple beam bridges can't span more than a few dozen feet without collapsing under their own weight. To cross anything wider, anything deeper, anything more ambitious, engineers needed a fundamentally different approach. They needed a way to redirect force that didn't rely on the stiffness of a beam. They needed to stop fighting the square cube law and start working around it. And the solution they found, the first great leap in bridge engineering, came from a shape so elegant, so structurally perfect, that it seems almost like it was designed by the universe itself. The arch. Here's something wonderful about an arch. When you look at one, when you see a stone arch bridge spanning a river, it looks like magic. It looks like the stones are just floating there, hanging in the air, held up by nothing. There's no beam underneath them. There's no rope above them. There's just this curve of stone. And somehow, it carries the weight of a road and the traffic on that road. And it does it so gracefully that you might not even wonder how. But if you do wonder how, the answer is beautiful. And it all comes back to our question: where does the weight go? In a beam bridge, force travels horizontally through the beam and then pushes down into the supports at either end. The beam is doing the work of holding things up by resisting bending, by being stiff enough to span the gap without sagging. An arch does something completely different. In an arch, force doesn't travel horizontally. It travels along the curve of the arch, following the stones, and it pushes outward and downward into the banks on either side. The arch isn't resisting bending, it's channeling compression. Every stone in the arch is being squeezed by the stones on either side of it, and that squeezing pushes the force along the curve further and further until it reaches the foundations at the base of the arch, where it pushes into solid ground. Think about it this way. Imagine you're standing in a line of people, shoulder to shoulder, and everyone leans inward. If the people at the ends have something solid to lean against, a wall maybe, then the whole line stays up. Nobody falls. The force of everyone leaning is transmitted through the line, person to person, until it reaches the wall. Now bend that line into a curve, an arc. The same thing happens, but now the force is traveling along the curve, and the walls at the ends have to resist not just a downward push, but an outward push as well. That outward push is called thrust, and it's the key to understanding how an arch works. The arch is constantly trying to flatten itself out, to push its foundations apart. And the foundations have to be strong enough to resist that push. If the foundations hold, the arch stands. If they don't, the arch collapses outward. And this is why arch bridges need something that beam bridges don't. They need what engineers call abutments. Massive anchoring structures built into the banks on either side, strong enough to absorb the outward thrust of the arch without moving. Now, the arch as a structural idea is ancient, really ancient. Builders in Mesopotamia were using arched structures thousands of years before the Common Era. But the people who perfected the stone arch, who turned it into a technology capable of spanning vast distances and lasting for millennia, were the Romans. And the structure that best represents their mastery, the one that still stands in the south of France after nearly 2,000 years, is the Pont du Gard. The Pont du Gard isn't just a bridge.
It's an aqueduct bridge, built to carry water across the valley of the Gardon River to the city of Nîmes. And it's enormous, 160 feet high, about 900 feet long, with 3 tiers of arches stacked on top of each other. The bottom tier has 6 arches, the middle tier has 11, and the top tier, where the water channel runs, has 35. When you stand below it and look up, it's overwhelming. The scale of it, the precision of the stonework, the sheer ambition of placing this structure in the middle of a river valley nearly 2,000 years ago. The Romans built it in the middle of the 1st century of the Common Era, during the reign of Claudius or possibly Nero. And they built it for a specific, practical reason. The city of Nîmes needed water. Now, Nîmes was one of the largest cities in Roman Gaul, with about 20,000 inhabitants. And the water source the engineers chose was a spring at a place called Uzès, roughly 30 miles away.
30 miles isn't particularly far, and the Romans were very good at building aqueducts. They'd built hundreds of them across the empire. But here's the problem that made this particular aqueduct one of the most challenging engineering projects of the ancient world. The spring at Uzès was only about 56 feet higher than the arrival point in Nîmes. 56 feet of elevation drop over 30 miles. That works out to a gradient of about 1 inch per 330 feet. A slope so gentle that if you laid a ruler along it, you'd have trouble seeing the tilt. And water doesn't flow without a slope. No slope, no flow. So the Romans had to maintain this incredibly precise, incredibly gentle gradient along the entire 30-mile route. Over hills, through valleys, across the Gardon River. Any mistake, any stretch that was too flat or too steep would either stop the water entirely or send it rushing too fast, eroding the channel.
The precision they achieved is almost unbelievable. Modern surveys of the aqueduct have measured gradients as gentle as about 1/25 of an inch per 13 feet in some sections. Without any modern surveying equipment, without lasers, without GPS, with nothing but plumb lines and water levels, and the geometry they learned from Greek mathematicians. These engineers maintained a consistent water flow across 30 miles of terrain that included one of the deepest river valleys in the region. And at the Pont du Gard itself, where the aqueduct had to cross that valley, the gradient became particularly tricky. The bridge section was essentially flat compared to the sections before and after it. Water moved much more slowly across the bridge, which meant it rose higher in the channel. The original designers didn't fully account for this. When the aqueduct was first put into service, the water actually overflowed the channel walls at the Pont du Gard. You can still see where they had to raise the walls, adding extra masonry on top of the original construction to contain the slower-moving water. To put that gradient in perspective, imagine a road that drops 1 inch over the length of a football field. Now imagine maintaining that exact slope consistently for 30 miles, across terrain that includes hills, valleys, and a river gorge, without any margin for error. Because if the gradient is too flat, the water stops. If it's too steep, it erodes the channel. The Romans hit this impossibly tight tolerance using nothing but surveying tools that would fit in a backpack. Think about what that means. These engineers, working 2,000 years ago, built an aqueduct so precise that the only error they made was a subtle miscalculation about how water behaves
when the slope changes slightly. They got the big things right: the arches, the structure, the route, the gradient. They just slightly underestimated the fluid dynamics across the bridge. And they fixed it. But let's get back to the arches themselves, because the structural engineering of the Pont du Gard is where our question, where does the weight go, gets its first truly satisfying answer. Each arch in the Pont du Gard is a semicircle. The Romans loved semicircular arches because they're geometrically perfect. Every stone in a semicircular arch is cut to a wedge shape, wider on the outside edge than the inside, so that when they're all fitted together, they lock into place. The force of gravity pushes each stone downward, but because the stones are wedge-shaped, that downward push gets redirected sideways along the curve into the neighbouring stones, which redirect it further, until it reaches the massive piers at the base of each arch. And those piers are doing something important. They're not just holding up the arches above them, they're also absorbing the outward thrust. Each pier has to resist the push of the arches on either side of it. And because those pushes are roughly equal and opposite, they mostly cancel each other out. The pier just has to stand there and be heavy and solid. The outward push from the arch on the left is balanced by the outward push from the arch on the right. But at the very ends of the bridge, where there's only one arch pushing outward, the force has nowhere to be balanced. That's where the abutments come in. The massive foundations built into the riverbanks. They absorb the thrust of the end arches and send it into the earth. So the complete path of force through the Pont du Gard looks like this. Weight pushes down on the top of the bridge. That weight travels through the stones of the upper arches, along their curves, into the piers below. Those piers carry the weight down to the next tier of arches, which redirect it outward again, into the next set of piers, and so on, tier by tier, until the force reaches the bottom piers, which are founded on the bedrock of the river valley. At every stage, force is being channeled through compression, through stones squeezing against each other, following the curve of the arches, until it reaches the ground. And here's how the Romans actually built these arches, because the construction process is as impressive as the finished product. To build a semicircular arch, you first need a temporary wooden support called centering. This is essentially two wooden semicircles, the same shape as the intended arch, joined together to form a sturdy framework. The centering rests on the piers below and provides a surface for the stone blocks to sit on while the arch is being assembled. The masons would lay the wedge-shaped stones, called voussoirs, on the centering, starting from both sides simultaneously and working upward toward the crown. The stones were cut precisely so that they would interlock when pressed together. But during construction, before the last stone was placed, the arch was not yet an arch. It was just a collection of stones balanced on a wooden scaffold. The structure only became self-supporting when the final stone, the keystone, was wedged into the very top of the arch. The moment the keystone went in, the arch came alive. All the stones locked against each other. The compression travelled from stone to stone, and the centering could be removed. The arch stood on its own. Before the keystone, a pile of stones on a scaffold. After the keystone, a self-supporting structure that could stand for millennia. That single stone made the difference. The Pont du Gard was built using limestone quarried from nearby deposits and cut by hand. The precision of the stonework is extraordinary. Many of the blocks weigh several tons each, and they were fitted together without mortar.
No cement, no adhesive, just precisely cut stone surfaces pressed together under their own weight. The sheer accuracy of the cuts was enough to create a stable, watertight joint. And here's what's really remarkable. This system has been working continuously for nearly 2,000 years. The aqueduct supplied water to Nîmes for about 500 years until the fall of the Roman Empire. After that, the water stopped flowing, but the bridge itself kept standing. Through the medieval period, through the Renaissance, through wars and floods and earthquakes, the Pont du Gard endured. Some of the stones have shifted slightly. Some repairs have been made over the centuries, but the basic structure, the arches, the piers, the foundations, they're still doing their job, still channeling force, still answering the question. The Romans built other arch bridges, hundreds of them, across Europe and the Mediterranean.
And they understood something about arches that wouldn't be formally articulated for another 1,700 years. They understood that arches work best when they're part of a system. When you have a series of arches side by side, each one helps stabilize its neighbors. The thrust from one arch pushes into the pier, and the thrust from the next arch pushes back. They balance each other. The whole structure becomes stronger than any individual arch would be on its own. But there was a limit to what the Romans could do with stone arches. And it was the same limit that plagues beam bridges, just in a different form. Stone is incredibly strong in compression. You can squeeze it, pile weight on top of it, and it will resist beautifully. The Pont du Gard's piers carry thousands of tons without complaint. But stone is weak in tension. Pull it apart, stretch it, and it cracks. And this limits how wide a single stone arch can span.
As the span increases, the stones at the top of the arch, near the crown, begin to experience some tension on their inner surfaces, especially under uneven loads. For a semicircular arch, the practical limit was about 130 feet. Push much beyond that, and the weight of the stone itself, combined with the tension at the crown, would cause the arch to crack and collapse. 130 feet is impressive, but it's not enough to cross a wide river. It's not enough to span a deep gorge, and it's nowhere near enough for the kind of crossings that the modern world would eventually demand. For over 1,000 years after the fall of Rome, the art of bridge building went through a long, quiet period where progress essentially stalled. When the Roman Empire collapsed, the institutional knowledge that had built the Pont du Gard and hundreds of other magnificent structures was scattered and largely lost. The centralized engineering corps, the trained workforce, the supply chains for quarried stone, all of it dissolved in the chaos of the early medieval period. Bridge building didn't stop entirely, of course. Communities still needed to cross rivers, and the church, as the most powerful institution in medieval Europe, sponsored many bridge projects. In fact, the word pontiff, the title used for the Pope, literally means bridge builder, from the Latin pontifex. Whether or not the connection is more than etymological, the church invested heavily in bridges throughout the medieval period, funding their construction as acts of charity and piety. But structurally, medieval bridges were not advances on Roman design. They were, at best, competent reproductions, and at worst, clumsy imitations. The semicircular arch was the standard form. The piers were thick and heavy, often so wide that they blocked a significant fraction of the river's flow, causing the water to speed up between the piers and scour the foundations, which led to frequent collapses. Some medieval bridges were remarkable for their ambition rather than their engineering. The Old London Bridge, completed around 1209, was over 900 feet long with 19 arches, and it became famous not for its structural design, but for the city that grew on top of it. Houses, shops, a chapel, and even a public privy were built on the bridge deck, turning it into a street in the air. At one point, over 200 buildings crowded the bridge, leaning over the river on both sides, sometimes touching overhead. The weight was enormous, and the bridge required constant maintenance to keep it standing. It lasted over 600 years, but more through persistent repair than brilliant engineering. The Ponte Vecchio in Florence, completed in 1345, is another bridge from this era that survives today, with its famous shops, mostly jewelers now, lining both sides of the deck. Structurally, it's a three-arch bridge built of stone, competent but unremarkable. Its fame comes from its age, its beauty, and its history, not from any engineering innovation. The real breakthrough, the first significant advance in bridge engineering since the Romans, came in the 18th century, and it came, appropriately, from France, the country that would produce more great bridge engineers over the next 3 centuries than any other nation on Earth. Then, in the late 1700s, a French engineer did something that nobody had done before. He actually sat down and figured out mathematically how an arch bridge really works. His name was Jean-Rodolphe Perronnet, and he's sometimes called the father of modern engineering. Perronnet was the first director of the École des Ponts et Chaussées, the world's first engineering school, founded in Paris in 1747. And he brought to bridge building something that the Romans, for all their genius, never had: a systematic, mathematical understanding of how forces flow through a structure. What Perronnet realized was something that seems obvious once you hear it, but that had eluded builders for centuries. In a multi-arch bridge, the arches don't work independently. They work together. The thrust from each arch is transmitted through the piers to the neighboring arches, and the whole bridge behaves as a single, interconnected system. This had a revolutionary practical implication. If the arches are sharing their thrust through the piers, then the piers don't need to be nearly as thick as traditional Roman engineering demanded. You could make the piers much slimmer, much more elegant, because the thrust was being passed along, arch to arch, all the way to the abutments at the ends. Perronnet halved the thickness of his bridge piers, compared to conventional design. His bridges were lighter, more graceful, used less material, and yet they were structurally sound because he understood the flow of force through the complete system, not just through individual arches. He also moved beyond the semicircular arch. Perronnet used elliptical arches, flatter and wider, which could span greater distances with less material. These arches looked dramatically different from the heavy, round arches of Roman and medieval bridges. They were slender and elegant, almost impossibly thin, and they represented a genuine leap forward in engineering. Perronnet's work opened the door to longer, lighter, more ambitious stone bridges. But even with his innovations, stone was reaching its limits. An elliptical arch could span further than a semicircular one, but the fundamental problem remained. Stone is heavy. Stone is strong in compression, but weak in tension. And the square cube law meant that as spans grew longer, the weight of the stone grew faster than the strength of the structure. To go further, to span the hundreds and eventually thousands of feet that the industrial world would demand,
Engineers needed something that stone could never provide. They needed a material that was strong in both compression and tension. A material that was lighter than stone. A material that could be shaped into forms that stone couldn't hold. They needed iron. And iron was about to change everything. Let me tell you why iron changed the world of bridges so dramatically. Because it's really about a single physical property that stone and wood simply don't have. Iron is strong in tension. That might not sound like much when I say it out loud, but think about what it means. For 3,000 years, every bridge on Earth was built from materials that could only handle compression well. Stone, brick, wood to some extent. And because those materials could only really push against each other, they were limited to shapes that kept everything in compression. Arches, thick beams, massive piers. Everything had to be squeezed together, packed tight, because if any part of the structure got stretched, got pulled apart, it would fail. Iron changed that. Iron could be pulled without breaking. You could stretch it, hang weight from it, put it in tension, and it would hold. And not just hold, but hold with astonishing strength. Pound for pound, iron was about 60 times more resistant to compression than stone, and it could handle tension that stone couldn't handle at all. This meant, for the first time in history, that bridge builders weren't limited to arches. They could build shapes that included members in tension. They could build triangles. And the triangle turned out to be one of the most important shapes in the history of engineering. Here's why triangles matter. If you make a square out of 4 rigid bars and pin them together at the corners, the square isn't stable. Push on one corner and the whole thing skews into a parallelogram. The bars are rigid, but the shape can deform because the angles at the corners can change. But a triangle is different. If you make a triangle out of 3 rigid bars and pin them together, the shape is locked. You can push on any corner and the triangle won't deform. The only way to change its shape is to bend or break one of the bars. The geometry itself provides stability. This property makes triangles the perfect building block for structures called trusses. A truss is essentially a framework of triangles fitted together, each triangle sharing sides with its neighbours, creating a structure that's incredibly stiff and strong relative to its weight. And in a truss, the force path is clear and elegant. Some members are in compression, being pushed together. Others are in tension, being pulled apart. And the triangular arrangement ensures that every force is balanced, that nothing can move without something else resisting it. The first iron bridge in the world was built in 1779 at Coalbrookdale in England. A cast iron arch spanning about 100 feet across the River Severn. It was a proof of concept, a demonstration that iron could be used as a structural material for bridges. But the real revolution came in the early 1800s, when engineers began to understand that iron didn't need to be used in the shape of an arch. Iron could be used in trusses, in beams, in frameworks of any shape the engineer could imagine. And this opened up possibilities that stone builders couldn't have dreamed of. By the middle of the 19th century, the Industrial Revolution was reshaping the world. Railways were spreading across Europe and the United States at extraordinary speed. And railways needed bridges. Lots of bridges. Bridges across rivers, bridges across valleys, bridges that could carry the immense weight of a locomotive and its train of loaded cars. And those bridges needed to be built quickly, efficiently, and at spans that would have been impossible in stone. Iron and then steel, which is an alloy of iron and carbon with far superior mechanical properties, made this possible. Steel could be shaped into beams, rolled into plates, drawn into wire. It could be riveted together or eventually welded. And it enabled a new generation of bridge builders who thought in terms of force and structure rather than mass and weight. One of the most remarkable of these new iron and steel structures, one that shows just how far engineers had come from the heavy stone arches of the Romans, is the Garabit Viaduct in the heart of the Massif Central in France. And the man who designed it needs no introduction, though you might not know him as a bridge builder. His name was Gustave Eiffel. Before the Eiffel Tower made him a household name, Eiffel was one of Europe's most prolific bridge engineers. He built over 100 bridges and viaducts across France and around the world, and his signature style was unmistakable. Eiffel used lattice trusses, open frameworks of iron arranged in triangular patterns that were simultaneously strong and lightweight. His structures had a distinctive lacy quality, as if they were woven from metal threads, and this wasn't just an aesthetic choice. The open lattice allowed wind to pass through the structure instead of pushing against a solid surface, which dramatically reduced the forces that the bridge had to resist. The Garabit Viaduct, completed in 1884, was Eiffel's masterpiece before the tower.
It's about 1,850 feet long and nearly 400 feet high, carrying a railway across the gorge of the Tuyere River. The main arch spans over 540 feet, and the whole thing is made of wrought iron lattice work. It's breathtaking to look at. The structure seems impossibly delicate for something that carries trains. The iron members are thin, the connections are precise, and the overall impression is one of engineered elegance, of every piece being exactly where it needs to be, and not a gram of material more than necessary. And here's something worth knowing about Garabit. Before Eiffel built his viaduct, there was nothing in the valley. No roads, no infrastructure, no access. The construction team had to build roads just to get to the site, then build housing for the workers who would assemble the viaduct.
The whole operation was carried out in one of the most remote, rugged parts of France, and it was completed in just 4 years, an incredible feat for the 1880s. The construction of the Garabit Viaduct is a story in itself. Half of the wrought iron was pre-assembled at workshops in the Val de Meuse near Paris, then transported to the remote site. The other half was assembled on location using hot riveting, the same technique that would later be used on the Golden Gate Bridge. Workers heated iron rivets to red or white hot, inserted them through holes drilled in the overlapping girder plates, and hammered the tail flat. As the rivet cooled, it contracted, pulling the plates together with thousands of pounds of clamping force. Each rivet was a permanent, incredibly strong connection, and the Garabit Viaduct contains thousands of them. When the bridge was completed, it wasn't just celebrated in France, it was marveled at internationally, especially in the United States, where engineers recognized it as a breakthrough in long-span iron construction. It remains one of the 2 most famous structures Eiffel ever built. The Garabit Viaduct was also Eiffel's testing ground for the lattice girder technology that he would use, just a few years later, for the Eiffel Tower. The same triangulated iron framework, the same emphasis on lightness and wind resistance, the same engineering philosophy. The tower was, in many ways, a vertical bridge, and Eiffel's experience building bridges is what made it possible. But while Eiffel and engineers like him were pushing iron and steel to new heights,
Something darker was happening across the Atlantic. In the United States, the railway boom of the late 19th century was demanding bridges at a pace that quality couldn't always match. Bridges were being built quickly, often cheaply, with cast iron that hadn't been properly tested and designs that hadn't been properly calculated. And cast iron, unlike the wrought iron Eiffel favoured, has a dangerous weakness. It's brittle. Under sudden loads, under vibrations, under the repeated stress of trains passing overhead day after day, cast iron can crack without warning. In the 1880s alone, nearly 200 bridges collapsed in the United States. 200. Some of them fell while trains were crossing, killing dozens of people. The disasters were so frequent, so devastating, that they fundamentally changed how Americans thought about bridge safety. Engineers began to understand that iron, for all its strengths, could fail in ways that stone never did. Stone crumbles slowly. Iron snaps. These failures pushed the industry towards steel, which was stronger, more ductile, and more predictable than cast iron. Steel could be tested and certified.
Its properties could be calculated in advance. And crucially, steel could be welded, which meant that the riveted joints that were often the weakest points in an iron structure could eventually be replaced with continuous, solid connections. The transition from iron to steel in the late 19th century was, in the world of bridges, as significant as the transition from stone to iron had been a few decades earlier. Steel opened the door to the truly colossal bridges of the 20th century, the suspension bridges that would span not hundreds but thousands of feet, carrying highways and railways across obstacles that would have seemed impassable just a generation before. But before we get to suspension bridges, I want to go back to our central question. Where does the weight go in an iron or steel truss bridge? The answer is surprisingly elegant. In a truss bridge, the road deck sits on a framework of triangulated members. When a truck drives across the bridge, its weight pushes down on the deck, which transfers the load into the truss members. Some of those members are in compression, being squeezed together, and they push the force toward the supports. Others are in tension, being stretched, and they pull the force toward the supports. The combination of pushes and pulls, channeled through the triangular geometry, sends all the force to the piers at either end of the span. And here's the clever part. Because the truss is made of triangles, each member carries force along its own length, in a straight line, either being pushed or pulled. There's very little bending. And bending, as we learned with the simple beam, is the enemy. Bending means the top of a member is in compression while the bottom is in tension, and that's inefficient. A truss avoids this by breaking the structure into individual members that each do one job, either push or pull. The result is a structure that can span much farther than a solid beam of the same weight, because the material is being used more efficiently. This is why you see truss bridges on railways, on highways, across wide rivers. The Warren Truss, the Pratt Truss, the Howe Truss, each one a different arrangement of triangles optimized for different loading conditions. They're all doing the same thing, channeling force through compression and tension along triangulated paths until it reaches the ground. And there's a beautiful demonstration of this principle that's over 130 years old, from the Forth Bridge in Scotland. When Benjamin Baker wanted to explain his cantilever bridge design to the public, he staged a photograph that became one of the most famous images in engineering history. He had two men sit in chairs, extending their arms outward, each holding a long stick. A third man sat on the sticks between them, suspended in the air. The men's arms were in tension, being pulled by the weight of the man in the middle.
The sticks were in compression, being pushed inward, and the chairs provided the foundation, absorbing the force and transmitting it into the ground. The whole arrangement was a perfect miniature of how a cantilever bridge works: tension on top and compression on the bottom, the opposite of a simple beam. Baker's demonstration team recreated this arrangement for a modern audience recently, using the same setup, the same positions, and the same physics. The forces remain true today. What worked in 1887 works now. Some things in engineering don't change. The key takeaway about trusses is that they changed the question of bridge design from how do I make a beam stiff enough to span this gap, to how do I arrange the force paths so that every member is doing either a pure push or a pure pull. A truss bridge doesn't fight bending, it eliminates bending.
And that makes it dramatically more efficient per pound of material. But steel trusses, like stone arches and wooden beams before them, have their limits. A steel truss can span several hundred feet, maybe even 1,000 if it's big enough. But as spans grow longer, the truss gets heavier and the square cube law starts to bite. At some point, you need so much steel to hold up the truss itself that adding more span becomes impractical. To cross the really big gaps, the mile-wide rivers and the deep ocean straits, engineers needed yet another idea. They needed to stop channeling force horizontally through beams or trusses and start channeling it vertically through something that could carry enormous loads in tension without being heavy. They needed cables. And cables, strung between towers and draped in graceful curves, would give rise to the most dramatic, most beautiful, and most challenging type of bridge ever conceived: the suspension bridge.
Here's something that might seem counterintuitive at first. The longest bridges in the world, the ones that span the greatest distances between their main supports, are not the heaviest bridges. They're among the lightest. And the reason is that they use a structural principle that flips everything we've talked about so far upside down. Almost literally. In a beam bridge, force travels horizontally through the beam by bending. In an arch bridge, force travels along the curve of the arch by compression. In both cases, the structure is essentially rigid. It holds its shape through stiffness. A suspension bridge does something radically different. The main structural element, the cable, isn't rigid at all. It's flexible. If you hung a cable between 2 points and let it drape under its own weight, it would form a curve, a catenary curve, the shape that a chain makes when you hold it at both ends and let it sag.
And if you hung weight from that cable at regular intervals, the curve would change slightly, becoming closer to a parabola. That cable isn't resisting bending. It isn't in compression. It's entirely in tension. Every fibre of the cable is being pulled, stretched, subjected to the same pulling force from one end to the other. And tension is something that steel handles extraordinarily well. A steel cable can carry enormous loads in pure tension, far more than a steel beam of the same weight can carry in bending. So the force path in a suspension bridge is fundamentally different from anything we've seen before. Weight pushes down on the road deck. That weight is carried by vertical ropes called suspenders that hang down from the main cables. The suspenders pull on the cables, which are in tension. The cables drape over the tops of tall towers, and the downward pull of the cables pushes down on the towers, which are in compression. The towers carry the weight down into their foundations, into the bedrock, into the earth. Meanwhile, the horizontal tension in the cables, the force that wants to pull the cable ends together, is resisted by massive anchorages built into the ground at either end of the bridge. So the complete force path goes like this. Weight goes down into the suspenders. Suspenders pull on the cables, which carry the force upward and outward to the towers. The towers push the force straight down into the earth, and the horizontal pull of the cables is absorbed by the anchorages, which are so heavy and so deeply embedded in the rock that they can resist millions of pounds of lateral force. 4 points where the entire weight of the bridge meets the ground. 2 towers and 2 anchorages. That's it. A bridge that might be a mile long, carrying thousands of vehicles, weighing hundreds of millions of pounds. All of that force funneled to just 4 contact points with the earth. Now, suspension bridges as a concept are very old. Primitive rope bridges have been used in mountainous regions for centuries, probably millennia. But the modern suspension bridge, the kind that uses steel cables and can span enormous distances, is really a product of the 19th century. And the story of how it developed is inseparable from the story of one extraordinary family, the Roeblings. John Augustus Roebling was born in 1806 in the Prussian city of Mühlhausen. He studied engineering at the Royal Polytechnic Institute in Berlin, and in 1831 he emigrated to the United States. He settled first in a small farming community in western Pennsylvania. But farming didn't suit him. He was an engineer, and America in the 1830s and 40s was a country building itself from scratch, hungry for engineers. Roebling made his first great contribution to bridge engineering, not by designing a bridge, but by inventing something a bridge would need: wire rope. Before Roebling, most cables were made of hemp or chain. Hemp was light but weak. Chain was strong but heavy and rigid. Roebling figured out how to spin thin steel wires together into cables, creating a material that was both incredibly strong in tension and relatively light. He patented the process and built a factory to produce wire rope, and it made him wealthy. But he wanted more. He wanted to build something legendary. His chance came with the Brooklyn Bridge. By the middle of the 19th century, the cities of New York and Brooklyn, which at that time were separate municipalities, were separated by the East River. The only way to cross was by ferry, and the ferries were overcrowded, unreliable, and occasionally deadly. In winter, ice could shut them down entirely. A bridge was needed. But the East River at the proposed crossing point was over 1,600 feet wide, with a busy shipping channel that required high clearance for masted vessels. The bridge would need towers nearly 300 feet tall, the tallest structures in North America at the time. Roebling designed the Brooklyn Bridge as a suspension bridge with a main span of 1,595 feet, longer than any bridge in the world. The 2 towers would be made of limestone and granite, and they would carry 4 massive cables, each nearly 16 inches in diameter, composed of thousands of individual steel wires. The road deck would hang from these cables on vertical suspender ropes, and the cables would be anchored in enormous stone and concrete anchorages on either shore. But before construction could even begin, tragedy struck. In the summer of 1869, while surveying the site for the Brooklyn Tower, Roebling was standing at the edge of a dock when a ferry boat came in and crushed his foot against a piling. The injuries were severe. Roebling refused medical treatment beyond having water poured on the wound, and within weeks, he had developed tetanus. He died on July 22nd, 1869, at the age of 63. He never saw a single stone of his bridge laid. His son, Washington Roebling, took over as chief engineer. Washington was 32 years old, a Civil War veteran, and he'd studied bridge engineering in Europe before the war. He was capable, determined, and deeply committed to realizing his father's vision. The first and most dangerous phase of construction was sinking the foundations for the two towers. The towers had to rest on solid bedrock, which in the East River lay deep beneath layers of mud and silt. To reach the bedrock, Washington Roebling used a technology called pneumatic caissons, essentially giant wooden boxes, about 170 feet long by 100 feet wide, that were sunk to the riverbed and then filled with compressed air to keep the water out. Workers, called sandhogs, climbed down into these pressurized chambers and dug through the mud and rock, sending debris up to the surface through shafts, while the immense weight of the granite tower blocks being stacked above gradually pushed the caisson deeper into the earth. The work was brutal. The caissons were cramped, dark, and filled with the constant noise of digging and the hiss of compressed air. Temperatures inside could reach over 100 degrees, and there was a danger that nobody fully understood at the time. Caisson disease, what we now call decompression sickness, or the bends. When workers spent long periods under high pressure and then returned to the surface too quickly, dissolved nitrogen in their blood would form bubbles, causing excruciating joint pain, paralysis, and sometimes death.
Washington Roebling spent extensive time in the caissons himself, working alongside his men, and in 1872 he suffered a severe case of caisson disease that left him partially paralyzed and in chronic pain. He was bedridden for much of the remaining construction period, unable to visit the bridge site. Instead, he watched the construction through a telescope from his bedroom window in Brooklyn Heights and communicated his instructions through his wife, Emily. Washington Roebling was confined to his bedroom for most of the remaining 11 years of construction. He could see the bridge from his window, and through a telescope he tracked every detail of the work. He wrote detailed instructions for each phase of the project, specifying materials, methods, sequences, and tolerances. But he could not deliver those instructions himself. He could barely leave his bed. Emily Warren Roebling became, in effect, the de facto chief engineer of the Brooklyn Bridge.
She studied mathematics, bridge design, and construction management. She communicated daily with the assistant engineers, translated Washington's technical instructions into actionable orders, and represented the project in meetings with city officials and contractors. Without Emily Roebling, the Brooklyn Bridge almost certainly would not have been completed. She was one of the first women to serve as a civil engineer in the United States, though the title was never officially given to her. The caissons eventually reached bedrock, the Brooklyn side at about 44 feet below the river surface, and the Manhattan side at about 78 feet. The towers rose, the cables were strung, and the cable spinning process that John Roebling had invented was used to create the 4 main cables, each one composed of 5,434 individual steel wires. And here's a detail about those cables that says everything about Roebling's engineering foresight. The Brooklyn Bridge was the first suspension bridge in the world to use galvanized steel wire. Galvanized means coated with zinc, a metal that oxidizes but doesn't rust. The zinc coating protects the steel underneath from corrosion, dramatically extending its lifespan. And it worked. The original cables of the Brooklyn Bridge are still in service today, over 140 years later. Engineers who have inspected them report that the galvanized wires are in excellent condition, and they estimate the cables could last another 200 to 300 years. To prove the bridge was safe, after one person tripped during the opening day celebration, and a panic about collapse led to a stampede that killed 12 people, Washington Roebling arranged for a herd of elephants to walk across the span. If the bridge could hold a parade of elephants, it could hold anything. The public was convinced. The Brooklyn Bridge opened on May 24, 1883. After 13 years of construction, 27 deaths, and the sacrifice of an entire family. John Roebling conceived it and died before it began. Washington Roebling built it and was crippled by it. Emily Roebling saved it and received too little credit for it. And the bridge itself became one of the most iconic structures in the world, an enduring monument to human ambition and the price it sometimes demands. But the Brooklyn Bridge also revealed something important about the force path in a suspension bridge. The force path depends on the anchorages. Those enormous stone and concrete blocks buried in the earth on either shore, they're what resist the horizontal pull of the cables. Without them, the cables would pull the towers inward and the bridge would collapse. The anchorages are the ultimate destination of the horizontal force, just as the tower foundations are the ultimate destination of the vertical force. And anchorages are expensive. They're massive. They require solid rock to push against. And in some locations, the rock isn't suitable. It's too soft, too crumbly, too far below the surface. This limitation would become critically important later when engineers tried to build bridges in places where anchorages simply couldn't work. But before we get there, let me take you to San Francisco. Because the Golden Gate Bridge, completed in 1937, is the suspension bridge that taught the world something about force that nobody had fully appreciated before. Not just the downward force of gravity, but the sideways force of wind. Joseph Strauss was not, by any conventional measure, qualified to build the world's longest suspension bridge.
He was a Chicago-based engineer who had made his career building bascule bridges, short, functional structures that tilt up over small canals and rivers. He stood about 5 feet tall, had a personality that his biographers describe as part visionary and part showman. And he had never designed a bridge longer than a few hundred feet. But Strauss had two things that mattered more than experience. He had ambition, and he had the ability to hire people who were smarter than he was. When the Golden Gate Bridge project came before him, Strauss recognized it as the opportunity that would define his legacy. He submitted a proposal to the city of San Francisco with a cost estimate of $25 million, 1/10 of what other engineers were quoting. The city accepted. But when officials saw his initial design, a heavy, ungainly structure based on his bascule bridge experience, they were unimpressed. One historian described it as widely considered ugly, on the verge of hideous. Strauss went back to the drawing board. And this time, he brought in help. Charles Ellis, a professor of structural engineering at the University of Illinois, and Leon Moisseff, one of the country's leading suspension bridge designers. It was Moisseff who brought to the project new theoretical approaches to suspension bridge design, and Ellis, who sat down with pencil, paper, and a hand-cranked adding machine and performed the staggering number of calculations needed to design the world's longest bridge in an era before computers. The design that emerged was a pure suspension bridge,
with a main span of 4,200 feet between the towers, 213 feet longer than the George Washington Bridge in New York, which then held the record. The towers would rise 746 feet above the water. Each of the two main cables would be over 7,000 feet long and nearly 3 feet in diameter, composed of more than 27,000 individual wires. But building this bridge was going to be extraordinarily difficult because the Golden Gate is one of the most hostile environments any bridge has ever been placed in. The strait is about 1.5 miles wide, and the water is deep, over 300 feet in some places, carved by millions of years of tidal flows. The currents are ferocious. Over 7 trillion gallons of water flow through the Golden Gate every day, twice in each direction, as the tides change, at speeds approaching 9 miles per hour. Winds can gust to over 60 miles per hour, and fog rolls through the strait almost daily. Thick, cold, wet fog that drops visibility to near zero and drops temperature by 30 degrees in hours. Strauss and his team started construction in January 1933, in the depths of the Great Depression. Unemployed men lined up along the shoreline below the bridge site, cooking beans and waiting for a chance to work. The pay was $5.50 a day, excellent wages at a time when 1 in 4 Americans had no job at all. The anchorages came first. Massive concrete foundations poured into excavations in the rock on either shore. For the concrete, Strauss's engineers made an innovation that sounds minor but proved crucial. They used high silica concrete, a mix designed to resist the corrosive effects of salt water. It was the first time this type of concrete had been used in a major bridge project, and it helped protect the anchorages from the relentless assault of the Pacific. The North Pier, on the Marin County side, was relatively straightforward. It was built on a bedrock platform about 20 feet underwater. But the South Pier, on the San Francisco side, was a nightmare. It had to be located over 1,100 feet from the shore, out in the middle of the ferocious currents of the Golden Gate. Workers first built a steel trestle to reach the site, but a ship rammed into it in the fog and wrecked it. Then a storm destroyed the rebuilt trestle. Strauss ordered it rebuilt again, 5 feet higher and reinforced with heavier steel. Then came the most dangerous phase, building the foundation 30 feet underwater on solid bedrock. Divers, in bulky, old-fashioned diving suits, descended into the murky, sediment-laden water. Below about 30 feet, the water was completely dark. Visibility was zero. The divers could only work during the 4 daily slack tides, about 20 minutes at a time, when the current briefly eased. Using blast tubes to direct black powder charges, the divers blasted the bedrock flat. A bucket crane cleared the rubble. It was the first time large-scale underwater blasting had been used for a bridge foundation. It was dangerous, slow, and exhausting work. But there was no other way to create a flat surface for the foundation. To protect the construction site from the currents, Strauss's team built a massive, watertight concrete fender around the pier location, an oval structure the size of a football field, weighing 9,000 tons. Once the fender was in place, pumps sucked out about 9.5 million gallons of water, leaving a dry hole in the middle of the Golden Gate. An engineer and a superintendent climbed down a ladder about 107 feet inside the fender, inspected the bedrock, and declared it solid. Strauss was overjoyed. The South Pier was completed on December 31st, 1934, right on schedule. Workers then began erecting the towers, each made of structural steel cells, about 3 feet square, riveted together in a honeycomb pattern that was both strong and light. This was another innovation.
Most suspension bridge towers before the Golden Gate were made of solid stone or heavy steel plate, making them rigid and massive. But the Golden Gate's designers knew they needed towers that could flex in earthquakes and high winds without breaking. The honeycomb structure gave them exactly that, strength with flexibility. Building the towers was dangerous work. Iron workers assembled 20,000 tons of steel in each tower, piece by massive piece, in winds that could reach 60 miles per hour and fog so thick they couldn't see their hands in front of their faces. The rivet gangs, teams of 4 men, drove 600,000 rivets into each tower. The process was brutal. Rivets had to be heated to white hot, passed to the riveter through a tube, driven into the hole while still molten, and then hammered flat on the other side.
Inside the tower cells, which were only about 3 feet square, the noise of the riveting guns was deafening, and the white-hot rivets melted the red lead paint off the steel, creating toxic lead fumes. When workers began suffering nausea and abdominal pain, classic signs of lead poisoning, Strauss took action. He ordered that all future steel be coated with iron oxide paint instead of lead. He had the existing rivet holes stripped of their lead paint. He pumped compressed air into the tower shafts for ventilation, and he provided all riveters with filter masks. In fact, safety was one of Joseph Strauss's most significant contributions to the Golden Gate Bridge project. On a $25 million construction job in the 1930s, conventional wisdom expected about 25 fatalities. Strauss was determined to do better. He required hard hats, a practice that was still unusual at the time. He issued safety goggles with tinted lenses to protect against glare. He installed safety lines and immediately fired anyone caught stunting or horseplay. And most famously, he strung a safety net beneath the entire length of the road deck during construction. That net saved 19 lives. Workers who slipped and fell were caught by the net and climbed back up. They called themselves the Halfway to Hell Club. But the safety record, remarkable as it was, did not hold to the end. On October 21, 1936, a traveling crane came loose and collapsed onto the bridge deck, crushing a worker named Kermit Moore. And then, on February 17, 1937, the worst disaster of the project struck. A construction platform broke free from beneath the half-finished roadway, carrying 13 men with it. The platform fell into the safety net, and for an instant the net held. Then it ripped free. Platform and men fell nearly 200 feet into the water. Only 3 survived. 10 men died. The tragedy devastated Strauss and the entire construction crew. But the bridge was structurally sound, and work quietly resumed. 2 months later, the roadway was complete. There's a particular detail about the Golden Gate Bridge that I find touching. As the bridge was being built, painters applied an orange-red primer to the steel as a temporary corrosion protection. This wasn't the intended final color, but the people of San Francisco, watching the bridge rise over the months and years, grew to love that warm, reddish-orange tone. Irving Morrow, the architect who designed the bridge's visual details, recognized its beauty and wrote to Strauss recommending it as the permanent color. He argued that the earthy tone would blend with the Marin headlands to the north and reflect the city of San Francisco to the south. The color is called International Orange, and it has become one of the most recognizable paint colors in the world. With the towers complete by the summer of 1935, work began on the cables. Workers from the John A. Roebling Sons Company, the same firm founded by the Brooklyn Bridge's designer, began spinning the massive main cables that would carry the entire bridge. Each cable would be nearly 3 feet in diameter, composed of over 27,000 individual wires, each about the thickness of a pencil, but too strong for a man to bend in half. Altogether, The two cables would contain over 80,000 miles of wire, enough to circle the Earth more than 3 times. The wires were strung using spinning wheels that travelled back and forth across the span, laying 2 wires at a time. At first, the process was slow, but the Roebling Company, facing a deadline that included financial penalties for every day of delay, developed a method of spinning from both ends simultaneously. The spinning wheels would meet in the middle of the span, exchange their wire loads, and return. The technique doubled the speed of cable spinning. Before long, workers were laying 1,000 miles of wire in a single 8-hour shift. The Roebling Company finished the cables months ahead of schedule. Once the wires were in place, they had to be compacted into a solid, cylindrical cable. Machines called cable compactors squeezed the thousands of loose wires together with over 160,000 pounds of pressure per ring, transforming the loose bundle into a dense, rigid cylinder. Metal cable bands were clamped around the cable every 50 feet, and the vertical suspender ropes that would hold up the road deck were attached to these bands. Finally, the cable was wrapped in wire, coated in primer, and painted with the same international orange as the towers. The road deck was built outward from each tower simultaneously, extending in both directions at once to keep the towers balanced.
Ironworkers moved steel beams into position in 4 directions at once, inching closer to the mid-span meeting point. Vertical suspender ropes, ranging from 10 feet to over 500 feet long, connected the roadway to the main cables at 50-foot intervals, separated by steel spreaders to prevent swaying. The Golden Gate Bridge opened on May 27, 1937, after 4 years of construction. 200,000 people walked across it on opening day. Some ran, some walked backward, some tap danced. One person crossed on stilts. A family wore matching cowboy outfits. It was a celebration of a city that had rebuilt itself after the earthquake of 1906, that had endured the Depression, that had dared to bridge the unbridgeable. Joseph Strauss attended the opening ceremony, but was visibly exhausted. Within a year, he suffered a heart attack and died. He was 68. Charles Ellis, the man who had done most of the structural calculations, received almost no recognition. Strauss had fired him 6 years earlier during a dispute over the schedule, and Ellis returned to academia. He died in 1949. It is not known whether he ever visited San Francisco to see the finished bridge. The Golden Gate Bridge has now stood for nearly 90 years. In 1989, it survived the Loma Prieta earthquake, a 7.1 magnitude event that caused nearly $7 billion in damage across the Bay Area. The bridge came through without structural damage, though engineers subsequently undertook a comprehensive seismic retrofit that took over a decade. They replaced the steel towers on the approaches, strengthened the foundations, and installed seismic isolation bearings at the tops of the landside towers. These bearings decouple the bridge deck from the towers during an earthquake, allowing the deck to move independently and reducing the forces transferred into the structure. And the bridge is still being maintained, constantly. There are about 35 painters employed full-time on the Golden Gate Bridge. They work in teams, each responsible for a different section, cleaning corroded steel, stripping old paint, applying 3 new coats. The harsh environment of the Golden Gate, the wind, the fog, the salt water, attacks the bridge constantly. There's a rule on the bridge. Any new piece of steel has to be painted within 2 hours of installation. Wait longer than that, and the salt and moisture in the air will begin corroding it. Behind the south approach, there's a yard that the bridge workers call the bone yard. It's the bridge's own repair shop, where corroded parts are brought back to life. A painter named Bob will take a rusted steel bar, sandblast it down to bare metal,
and recoat it with primer and top coat. An ironworker named Woody will take worn-out cable spreaders, the parts that keep the suspender cables from swaying in the wind, and recast them using zinc, a metal that doesn't corrode. The work is Sisyphean in the most literal sense. By the time the painting crew finishes one section of the bridge, the section they painted first has weathered enough to need attention again. The bridge will never be fully painted in the sense of having fresh paint everywhere at once. There will always be a section being cleaned, a section being primed, a section being top-coated, and a section beginning to weather. The painting of the Golden Gate Bridge is not a project with a beginning and an end. It is a process, a continuous, permanent, ongoing act of maintenance. And it's a reminder of something important about bridges that most people don't think about. A bridge is not a thing you build and then forget about. A bridge is a thing you build and then take care of forever, for as long as you want it to stand. The Golden Gate Bridge, like every bridge, is in a constant battle with time. The forces it was designed to carry, gravity, wind, seismic activity, those are all accounted for. But the slow, patient destruction of corrosion, of metal being eaten away by salt and moisture, atom by atom, that never stops. And the only defense is vigilance, inspection, painting, repair, year after year after year. But there's another enemy that the Golden Gate Bridge, and every suspension bridge, must contend with. And it's an enemy that destroyed a bridge just 3 years after the Golden Gate was built, in one of the most dramatic and instructive engineering failures in history. The Tacoma Narrows Bridge was a suspension bridge in the state of Washington, spanning a stretch of Puget Sound. It opened on July 7th, 1940, and almost immediately something was wrong. The bridge deck began to oscillate, not in the wind, but in very moderate breezes. The deck would rise and fall in gentle waves, like a ribbon being shaken. Local residents started calling it Galloping Gertie, and people came from miles around just to experience the bizarre roller coaster ride of crossing a bridge that was undulating beneath them. For 4 months, the bridge continued to oscillate. Engineers studied it, debated it, proposed fixes. Then, on November 7th, 1940, a wind of about 40 miles per hour began blowing through the Narrows. The bridge started its usual up and down oscillation, but then something changed. The motion shifted from vertical to torsional. Instead of rising and falling, the deck began to twist, one edge lifting while the other dropped, then reversing. The amplitude grew rapidly. Within an hour, the deck was twisting by nearly 30 feet from side to side. Then it tore itself apart. The center span ripped free from the suspender cables and fell 300 feet into Puget Sound. The only casualty was a dog, trapped in a car that its owner had abandoned on the bridge when the twisting became too violent. The collapse of the Tacoma Narrows Bridge remains, to this day, one of the most watched and most studied engineering failures in history. It was captured on film, and the footage is haunting. You can watch the deck twisting, rippling like a piece of cloth, one side rising while the other drops. The movement growing more and more violent until huge chunks of concrete road surface break free and fall into the water. And then the center span peels away from the suspender cables and drops, almost gracefully, 300 feet into the grey water of Puget Sound. The film is often shown in engineering schools as a vivid reminder that mathematics and intuition can fail. The designers of the Tacoma Narrows Bridge were not amateurs. They were experienced engineers who believed they had built a safe, sound structure. But they had overlooked something that the disaster would sear into the consciousness of every bridge engineer who came after them. What the collapse taught the world was something that engineers had not fully appreciated. Wind doesn't just push on a bridge. Wind can interact with a bridge's structure in complex ways, transferring energy into the bridge and causing it to oscillate at its natural frequency. If the oscillations aren't damped, if the bridge keeps absorbing energy from the wind faster than it can dissipate it, the oscillations grow until the structure fails. The Tacoma Narrows Bridge failed because its deck was too narrow and too shallow. It presented a flat, blunt profile to the wind, and the air flowing over and under the deck created alternating regions of high and low pressure that excited the torsional vibration mode. After the collapse, engineers began studying bridge aerodynamics in earnest. Wind tunnel testing became standard. Bridge decks began to be designed with streamlined profiles, shaped to let air flow smoothly around them without creating the pressure differences that cause oscillation. Every modern suspension bridge owes something to the lessons of Tacoma Narrows. The force of wind had been underestimated, not in magnitude, but in complexity. Wind doesn't just push, wind vibrates. And a bridge, if it's not designed to resist vibration, can shake itself to death. And now we can answer the question I posed at the beginning. Why does a Roman stone arch built 2,000 years ago still stand, while a modern steel bridge in Washington state destroyed itself in 4 months?
The answer comes down to how each bridge handled force. The Pont du Gard channels force through compression, stone squeezing against stone, along the curve of its arches, into massive piers and abutments founded on bedrock. Gravity pulls down, the arch redirects outward and downward, and the force arrives safely in the earth. The Romans never had to worry about wind because their arches are heavy, solid, and present no flat surface for the wind to grab. Wind flows around the stone. There's nothing to vibrate. The Tacoma Narrows Bridge, by contrast, was light and flat. Its deck was a shallow steel plate, 8 feet deep and 39 feet wide, with a profile like a blunt ruler turned sideways. It channeled the downward force of gravity beautifully through its cables and towers to the ground, but it had no answer for the sideways force of wind. The flat deck caught the air like a sail, and the aerodynamic forces set up vibrations that the structure couldn't damp. The Romans built for compression, and compression is stable. The Tacoma engineers built for tension, and tension is powerful, but fragile when paired with a shape that the wind can excite. 2 bridges, 2 force paths, and the one that forgot about the sideways force lost. It's a humbling reminder. The Romans didn't know the word aerodynamics. They'd never heard of resonance or flutter or vortex shedding. But they built in a way that made those problems irrelevant. Sometimes the oldest solutions are the most robust. Not because the ancients were smarter, but because the shapes they used, arches and mass and gravity, are inherently forgiving in ways that modern lightweight structures are not. The suspension bridge, for all its elegance, has a particular vulnerability. Those massive anchorages on either shore, the ones that resist the horizontal pull of the cables, they need solid rock, really solid. The cables of a major suspension bridge can pull with a force of hundreds of millions of pounds, and the anchorages have to absorb every bit of it. If the rock isn't strong enough, if it's crumbly or fractured or too soft, the anchorages can't hold, and the bridge can't be built. This constraint became a critical problem
in one of the most dramatic bridge projects of the 21st century. In the Guizhou province of southwestern China, engineers needed to span a canyon so deep that nothing like it had ever been bridged before. The floor of the valley was over 1,800 feet below the surface. The rock on either side was soft limestone, riddled with hidden caves and prone to landslides. There was absolutely no way to build anchorages in this kind of geology. And that meant a suspension bridge was impossible. But the people of Guizhou needed a bridge desperately. 35 million people lived in the region, and the only way to cross the valley was a treacherous 5-hour drive down a steep, winding road full of sharp rocks and landslide debris. The region was one of the poorest in China, partly because farmers couldn't get their goods to market efficiently. The valley wasn't just a geographical obstacle, it was an economic prison. The engineers needed a bridge design that didn't require anchorages, a design where all the force was channeled through the bridge itself, without needing to grab onto the rock at the ends. A design where the cables ran not from anchorage to anchorage, but from tower to deck and back again, all the tension contained within the structure. They needed a cable-stayed bridge. And to understand why that design works, we need to go back to London, to an obscure Victorian bridge that most people walk past without a second glance, and to the engineer who proved that the impossible was possible. In 1873, a British engineer named Roland Mason Ordish completed a bridge over the Thames in London that looked, at first glance, like a confused mess of cables and chains running every which way. It was called Albert Bridge, and it was 216 meters long, which is about 710 feet. It wasn't the longest bridge in London. It wasn't the tallest. It wasn't even the most visually striking. But it was, from an engineering standpoint, one of the most important bridges ever built. Because Albert Bridge was the first successful bridge to incorporate cable-stayed construction, and in doing so, it proved that a type of bridge that engineers had been trying and failing to build for 200 years could actually work. Let me explain what cable-stayed means and how it's different from a suspension bridge, because the distinction matters enormously for our question about where the weight goes. In a suspension bridge, the road deck hangs from vertical suspender ropes that are attached to a main cable. That main cable drapes between two towers in a graceful curve, and its ends are anchored in massive foundations on either shore. The weight of the deck pulls the main cable downward, and the tension in the cable pulls outward on the anchorages. The force path goes from the deck, up through the suspenders, along the main cable, down through the towers, and outward into the anchorages. In a cable-stayed bridge, there's no main cable. Instead, individual cables run directly from the road deck to the tower, like the spokes of an umbrella. Each cable is straight, not curved, and each one connects a specific point on the deck to a specific point on the tower. The weight of the deck creates tension in the cables, which pull on the tower, and the tower carries the force down into its foundation. Now, here's the crucial difference. In a suspension bridge, the horizontal pull of the main cable has to be absorbed by anchorages in the ground. In a cable-stayed bridge, the horizontal forces in the cables on one side of the tower are balanced by the horizontal forces in the cables on the other side. The cables on the left pull the tower to the left. The cables on the right pull the tower to the right. These forces cancel each other out, and the tower just has to resist the downward component, the vertical compression, which it sends into its foundation.
No anchorages needed. The horizontal forces balance within the structure itself. Tower just has to resist the downward component, the vertical compression, which it sends into its foundation. No anchorages needed. The horizontal forces balance within the structure itself. There's actually a helpful way to visualize the difference. Hold an umbrella upside down, with the handle pointing up. The ribs of the umbrella spread outward from the central shaft, like the cables of a cable-stayed bridge. The weight of the fabric pulls on the ribs, and the ribs push on the shaft. The shaft carries everything straight down. No outward thrust at the base. No need for anything to grab onto the ground laterally. Everything stays balanced because the ribs on one side push the shaft one way, and the ribs on the other side push it the other way. The shaft just goes straight down. That's a cable-stayed bridge in your hand. The road deck is the fabric. The cables are the ribs. The tower is the shaft. And the foundation catches the shaft's downward push, cleanly and simply, without any lateral struggle. One important detail about cable-stayed bridges that separates them from suspension bridges is the stiffness of the deck. In a suspension bridge, the deck can be relatively flexible because the main cable, draped in a graceful curve, provides most of the structural continuity. But in a cable-stayed bridge, the deck itself is a major structural element. It's being compressed by the horizontal components of the cable forces, squeezed from both ends like an accordion. This means the deck has to be designed to resist buckling, and it has to be stiff enough to distribute the loads evenly among the cables. It's one of the reasons that cable-stayed bridges tend to have deeper, stiffer deck sections than suspension bridges of similar span. That's the genius of the cable-stayed design, and that's why it's the only option when the geology won't support anchorages. The entire force path is contained within the bridge. Deck to cables, cables to tower, tower to foundation. No lateral force has to be transferred to the banks. But here's why it took over 200 years from concept to reality. The mathematics of a cable-stayed bridge are extraordinarily complex. In a suspension bridge, the main cable is a continuous element that carries force in a smooth curve, and calculating the forces in it is relatively straightforward. In a cable-stayed bridge, you have dozens or even hundreds of individual cables, each at a different angle, each carrying a different load, each interacting with every other cable through the tower and the deck. Change the tension in one cable, and you change the forces in all the others. One early bridge builder described it as a trigonometry nightmare, and he wasn't exaggerating. If even a single cable is over-tensioned or under-tensioned, the imbalance can cascade through the entire structure, leading to catastrophic failure. For 200 years, from the first cable-stayed designs proposed in the 1600s to Ordish's Albert Bridge in the 1870s, nobody could solve the mathematics reliably enough to build a pure cable-stayed bridge. Ordish was clever enough to know this, so he didn't build a pure cable-stayed bridge. He built a hybrid, combining cable-stayed elements with a conventional suspension system. Albert Bridge has a main cable, like a suspension bridge, with suspender ropes hanging down to the deck. But it also has diagonal cables running directly from the towers to the deck, cable stays which carry a portion of the load directly. The suspension system provided a safety margin, while the cable stays did part of the work.
If you stand on Albert Bridge and look carefully, you can see both systems working together. The curved main cable with its vertical suspenders and the straight diagonal cables converging on the towers. Two bridges in one. And Ordish's hybrid design demonstrated that cable stays could work, that you could run cables directly from a tower to a deck and trust them to carry load, even if you weren't yet confident enough to trust them with all of it. After Ordish, other engineers picked up the idea. Through the late 19th century and the first half of the 20th, cable-stayed designs were refined, the mathematics improved, and confidence grew. The invention of computers in the mid-20th century was transformative. Suddenly, engineers could calculate the complex interactions between dozens of cables, solve the trigonometry in seconds rather than months, and optimize every aspect of the design. By the 1960s and 70s, pure cable-stayed bridges were being built across Europe and Asia. They were lighter than suspension bridges, didn't need massive anchorages, and could be built relatively quickly. The cable-stayed design became the go-to solution for spans between about 500 and 3,000 feet, filling the gap between what beam bridges could do and what suspension bridges were needed for. And in the Pont de Normandie, completed in 1995 in France, cable-stayed construction broke through the 2,800-foot barrier, proving that this type of bridge could rival suspension bridges for long spans. But the most extreme test of cable-stayed engineering was still to come. And it came in the place where it was most desperately needed. The Beipanjiang Bridge, completed in 2016, crosses a canyon in Guizhou Province, China, that is so deep it makes your stomach drop just to think about it. The deck of the bridge sits 1,854 feet above the valley floor. That's higher than the top of the Empire State Building. It's so high that one World Trade Center could fit underneath it with room to spare. If you dropped a stone from the bridge deck, it would take nearly 11 seconds to hit the ground. The bridge is just over a mile long, with a main span of about 2,360 feet, making it one of the longest cable-stayed bridges on the planet. And it was built in a place where, by any rational assessment, a bridge should not exist. The canyon walls are steep, crumbly limestone, full of hidden caves and geological faults. The rock is so soft that you can crumble it in your hand. Landslides are common. The engineers who first surveyed the site described it as a nightmare. One of them later said that when they arrived, they weren't sure the bridge could be built at all. But 35.5 million people lived in the region of Guizhou, and the only way across the canyon was a 5-hour drive down a road that was dangerous even in good weather. Sharp rocks slashed tires. Steep gorges lined the road with sheer drops. Landslide debris regularly blocked the route. For the local farmers, getting goods to market was nearly impossible, and the poverty of the region was directly linked to this geographic isolation. A bridge would change everything. And the only type of bridge that could work in this geology, with its soft rock and hidden caves, was a cable-stayed bridge, one that didn't need anchorages in the crumbling canyon walls. The engineering challenges were staggering. First, the towers. The bridge needed 2 enormous concrete towers. The taller one, rising nearly 900 feet above the valley floor. And getting concrete to that height, in a location with no natural sand, was a problem nobody had solved before at this scale. The sand issue was solved first, with characteristic Chinese engineering ingenuity. There was no natural sand in the mountains around the construction site, but there was plenty of soft rock. So the engineers crushed millions of tons of rock into artificial sand. grinding it to precisely controlled grain sizes. Different grain sizes produced different strengths of concrete, and by controlling the sand, they could produce exactly the concrete they needed for each part of the bridge. Building the towers required a technique that goes back, remarkably, to a retired British judge with a passion for architecture. In 1885, a man named Andrew Peterson built what was then the tallest concrete structure in the world, a tower over 200 feet high in Hampshire, England. Peterson's tower, also known as Sway Tower, was built using a method called climbing formwork. The idea is simple but brilliant. You start with a set of molds at the base of the tower. You pour concrete into the molds. Once the concrete sets, you remove the bottom mold, lift it to the top, and pour the next layer. Then you remove the next bottom mold, lift it up, and pour again. The tower grows upward, one layer at a time, and you only need a few sets of molds to build a tower of any height. Peterson, an amateur with no engineering background, used just 3 sets of molds to build his entire tower. Each layer took about 2 days to fill and 2 days to cure before the bottom mold could be moved. The process took 6 years. But it worked. And if you look closely at Sway Tower today, you can still see the horizontal lines between each layer of concrete, each one representing 4 days of patient, methodical construction. At the Beipanjiang Bridge, the engineers used Peterson's climbing formwork technique on a vastly larger scale. The molds were assembled and positioned by hand, which allowed precise control over the complex H-shaped cross-section of the towers. As the towers grew taller, the concrete was initially lifted in large vats by tower cranes. But at greater heights, a different approach was needed. The artificial sand, being slightly rougher than natural sand, made the concrete harder to pump. So the engineers used high-pressure pumps capable of propelling thick concrete to heights of nearly 900 feet, defying gravity with raw hydraulic force. When the towers were finished, they'd consumed about 46,000 cubic yards of concrete, enough to fill about 16 Olympic swimming pools.
And you can still see the climbing formwork lines running all the way up, like the growth rings of a concrete tree. With the towers complete, the next challenge was the bridge deck. And here's where the problem of building in a deep canyon becomes particularly acute. The valley floor was over 1,800 feet below the bridge deck. You can't build scaffolding that high. You can't support the deck from below while you're assembling it. The deck has to support itself, somehow, as it's being built. The solution came from one of the most famous bridges in the world, one that had solved a similar problem 130 years earlier. The Forth Bridge in Scotland. The Forth Bridge, completed in 1890, is a cantilever bridge that crosses the Firth of Forth near Edinburgh. When it was built, it was the longest bridge in the world, about 8,200 feet from end to end, carrying a double-track railway on a structure so massive it still carries 200 trains and 3 million passengers a year, over 130 years later. Its designer was Benjamin Baker, one of the most important engineers in Victorian Britain, and Baker carried a very particular burden when he took on the Forth Bridge project. Just a decade earlier, in 1879, the Tay Bridge, in the same region of Scotland, had collapsed during a violent storm, killing all 75 people aboard a passenger train that was crossing at the time. The investigation into the Tay Bridge disaster revealed catastrophic failures. The designer, Thomas Bush, had drastically underestimated the wind loading.
The cast iron columns that supported the bridge were poorly manufactured, with defects that had been hidden by a technique called burning on, essentially patching cracks with molten metal instead of recasting the flawed parts. The bolt holes were rough, the bracing was inadequate, and the connections loosened over time under the cyclic loading of wind and trains. The Tay Bridge collapse was a watershed moment in engineering history. It forced the profession to take wind loading seriously and to demand much higher standards of construction quality. And it haunted Benjamin Baker. When he was given the fourth bridge project, which had originally been assigned to Bush himself before the Tay disaster scrapped that design, Baker was determined to build a structure that would leave absolutely no doubt about its strength. The fourth bridge is often said to be deliberately overbuilt, and Baker would not have objected to the description. After Tay, overbuilt was exactly what the public needed to see. Baker faced the same problem that the Beipanjiang engineers would face over a century later. The Firther Fourth was too deep and too muddy for scaffolding. The bridge had to be built without any temporary support from below. Baker's solution was elegant. He built the bridge symmetrically outward from each tower. Each time he added a section on one side of the tower, he added an identical section on the other side. The two sides balanced each other like a seesaw. The weight on the left was counterbalanced by the weight on the right, and the tower in the middle just had to resist the downward compression. No scaffolding needed. The bridge literally built itself, growing outward from the towers in both directions simultaneously, until the sections from adjacent towers met in the middle. Baker's method was revolutionary. It freed bridge construction from its dependence on scaffolding, making it possible to build bridges over any depth of water, any breadth of canyon, regardless of what was or wasn't below. At the Beipanjiang Bridge, the engineers adapted Baker's principle for cable-stayed construction. The deck was built outward from each tower, one section at a time, with cables added symmetrically to keep the forces balanced. Every time a new section of deck was attached on one side of the tower, a cable was added to support it, and a matching cable was added on the other side to maintain balance. The deck grew outward, section by section, supported entirely by the cables and the towers, with nothing below but 1,850 feet of empty air. And here's where the Beipanjiang engineers did something that had never been done before. Instead of building the main span beam by beam, assembling each piece of the deck individually over the void, they built deck sections on the ground, and then slid them underneath the growing span on rails. The sections were then lifted into position and welded to the end of the existing deck. This technique was twice as fast as the traditional beam-by-beam method, and in a location where every day of work at that altitude carried risk, speed was safety. After 42 months of construction, the two sides of the deck met in the middle. For the first time in history, the two sides of this massive canyon were joined. But before the bridge could carry traffic, there was one last engineering challenge. The main span, at 2,360 feet, was incredibly long for a cable-stayed bridge, and long spans flex. When heavy trucks cross a long bridge, the deck can sag under the load. If this happens repeatedly, the metal experiences fatigue, a gradual change in its crystal structure that makes it brittle and prone to sudden fracture. The solution was an orthotropic deck, and the concept is surprisingly easy to understand. Take a flat piece of cardboard and try to bridge a gap with it. It collapses immediately. It's not stiff enough. Now take a second piece of cardboard and fold it into a series of U-shapes, like a corrugated sheet. Place the flat piece on top of the corrugated piece and try the same experiment. Suddenly the bridge holds weight. The folded cardboard provides stiffness in the direction that matters, turning a floppy sheet into a rigid structure. An orthotropic bridge deck works the same way. The top plate, which the traffic drives on, is welded to a series of U-shaped ribs running along the bottom.
These ribs stiffen the deck so effectively that even at the center of the 2,300-foot main span, the deck barely flexes under the weight of a loaded truck. Inside the Beipanjiang Bridge, in an area normally off-limits to the public, you can see the orthotropic ribs running beneath the deck plate, row after row of steel U-channels welded to the underside of the road surface. They look simple, but they're the final piece of the puzzle, the detail that makes the world's highest bridge safe for daily traffic. The Beipanjiang Bridge carries 224 cables, the longest of which stretches over 1,250 feet. Each cable is made of up to 43 individual steel strands, bundled inside a waterproof casing. And each cable has a built-in gauge that continuously measures its tension. If any strand fails, engineers in a central control room can detect it immediately and schedule a replacement.
And here's a detail that shows just how carefully these engineers thought about every aspect of the design. In winter, Guizhou province is one of the most severely frozen areas in western China. At the altitude of the bridge deck, ice forms on the cables. On most cable-stayed bridges, the cables pass over the center of the roadway, directly above the traffic lanes. If ice builds up on those cables and then falls, it drops straight onto the cars below. A chunk of ice falling from several hundred feet could crash through a windshield and kill someone. The Beipanjiang engineers solved this with a brilliantly simple modification. They positioned the cables at the outer edges of the bridge deck, outside the traffic lanes. When ice forms and falls, it drops off the side of the bridge, into the canyon, far from any vehicle. It's the kind of detail that nobody outside of bridge engineering would ever notice.
But it's the difference between a bridge that works in summer and a bridge that works safely year-round in one of the harshest climates in China. There's one more detail about the Beipanjiang Bridge that I think captures the human side of this story. The bridge has a control center where engineers monitor the tension in all 224 cables in real time. If any cable's tension drifts outside its design parameters, alarms sound and maintenance teams are dispatched. The bridge is literally under constant surveillance, watched over day and night by engineers who understand that a cable-stayed bridge is a system of interacting forces, and that a change in one cable affects every other cable in the structure. The deputy chief engineer of the bridge, Leo Bohr, spent years of his life on the project, from the early design studies through construction and into the monitoring phase. He later said that when they first arrived at the canyon site and saw the scale of the challenge, the crumbling rock, the hidden caves, the sheer depth of the drop, he wasn't sure the bridge could be built at all. But they kept working, kept solving problems one by one, and when the bridge was finished, he described it as being like raising a child. You build it, you nurture it, and then it grows up and contributes to society. The Beipanjiang Bridge was completed in 2016. The drive across the valley that used to take 5 hours now takes about 4 minutes. The region's economy has begun to change. Farmers can get their goods to market. Children can get to better schools. Hospitals are reachable in emergencies. A bridge, in this case, didn't just span a canyon, it lifted a region. And the force path through this extraordinary bridge is entirely self-contained. Weight presses down on the orthotropic deck. The deck transfers the load to the cables, which are in tension. The cables pull on the towers, which are in compression. And the towers carry the force down through nearly 900 feet of reinforced concrete.
through the foundations, through the bedrock, and into the earth. No anchorages, no lateral thrust into the canyon walls, no dependence on the soft, cave-riddled limestone that would have made any other type of bridge impossible. Every pound of force enters the bridge at the top and exits at the bottom, through the towers, into the ground. Where does the weight go? Straight down, through two towers and into the heart of the mountain. But bridges aren't static. They don't just sit there holding weight. They vibrate, they flex, they expand and contract with temperature. They sway in the wind. They shimmy in earthquakes. And in the most extreme environments on Earth, engineers have had to design bridges that can survive forces that would tear a conventional structure apart. So far, we've been talking about force as if it's a steady, predictable thing. Weight pushes down. The bridge sends it sideways or down through arches, cables, and towers. And the earth absorbs it. Simple, clean, elegant. But in the real world, force is rarely that cooperative. Wind doesn't just push steadily on a bridge. It gusts. It swirls. It creates vortices that alternate pressure from one side to the other, setting up vibrations that can amplify until they tear a structure apart. We saw that at Tacoma Narrows. And earthquakes are far worse. An earthquake doesn't push in one direction. It shakes the ground in all three dimensions simultaneously. Sideways, forward and backward, up and down, at frequencies that can resonate with a bridge's natural vibrations. If a bridge is rigid, if it's designed to resist these forces by brute strength, the forces can exceed the bridge's capacity, and the structure cracks, buckles, or collapses. But if a bridge is flexible, if it's designed to move with the forces, to absorb the energy and dissipate it, then even enormous earthquakes and savage winds can pass through without doing permanent damage. The engineers call this the difference between resistance and resilience. A resistant structure fights the force head-on. A resilient structure lets the force pass through it, like water through a net. And the bridge that demonstrates this principle more dramatically than any other on Earth sits across the Gulf of Corinth in Greece, connecting the Peloponnese Peninsula to the Greek mainland. It's called the Rion-Antirion Bridge, and it was built in one of the most seismically active regions in Europe, directly over an active fault line where two tectonic plates are slowly pulling apart. The numbers are staggering. The Gulf of Corinth at the crossing point is about 1.5 miles wide. The water is over 200 feet deep. The seabed is loose silt and clay, with bedrock located somewhere around 3,000 feet down. 3,000 feet. That's over 1/2 mile of soft, unstable material between the surface and solid rock. No bridge in history had ever been built in conditions like these, and the project's chief designers, Jean-Paul Tessondier, and the structural engineering team have openly admitted that when they first saw the full scope of the challenge, they were tempted to close the file and refuse the project. But they didn't, and the solutions they came up with represent some of the most innovative bridge engineering of the 21st century. The first problem was the foundations. In a conventional bridge, you drive piles down to bedrock and build your piers on top of them. But bedrock at the Rion-Antirion site was over half a mile deep. Driving piles that far into soft clay was, in the words of one engineer, totally unfeasible and unrealistic. So the engineering team abandoned the conventional approach entirely. Instead of reaching down to bedrock, they decided to strengthen the seabed itself. Under each of the bridge's 4 massive pylons, they drove groups of 200 hollow steel pipes into the ocean floor. Each pipe was about 80 to 100 feet long and about 6.5 feet in diameter. These pipes didn't reach bedrock. They didn't need to. Their purpose was to compact and reinforce the soft clay, turning it into a more stable foundation. On top of these pipe groups, the engineers laid a bed of gravel about 10 feet thick, and on top of the gravel, they placed the bridge's foundations, called pier footings, which are among the largest ever constructed. Each footing is about 300 feet in diameter and divided into 32 compartments. And here's the remarkable part. The footings just sit on the gravel. They're not attached to the seabed. They're not bolted down. They rest on the gravel bed by their own enormous weight, held in place by friction and gravity. This seems counterintuitive. You'd think a bridge foundation would need to be firmly fixed to the ground. But at Rion-Antirion, a fixed connection would be a death sentence. In an earthquake, if the foundation were rigidly attached to the seabed, the shaking would transfer directly into the bridge structure, potentially tearing it apart. By letting the footings sit freely on a gravel bed, the engineers created a kind of shock absorber at the very base of the structure. During an earthquake, the footings can slide slightly on the gravel, reducing the forces transferred into the pylons above. The pylons themselves are single blocks of reinforced concrete, rising from the footings to support the bridge deck. And the deck, at about 1.5 miles long, is continuous from one end to the other. It doesn't rest on the pylons. It passes between them, suspended by 368 cable stays. And this is where the design gets really clever. Between each pylon and the bridge deck, there's a system of connections that looks nothing like anything you'd see on a conventional bridge. Instead of rigid bearings that lock the deck to the pylons, there are controlled failure devices, essentially engineered weak points that are designed to break in a specific, predictable way during a major earthquake. The system works like this. Under normal conditions, including moderate winds and small earthquakes, a rigid tube holds the deck in position relative to each pylon. The tube resists lateral movement, keeping the deck centered. But during a major earthquake, when the forces exceed a predetermined threshold, a fuse inside the tube breaks. The rigid connection is gone. And now a set of shock absorbers, similar in principle to the ones in your car, takes over. These absorbers allow the deck to move laterally, sliding up to about 12 feet relative to the pylons, while dissipating the earthquake's energy through controlled friction. Think about what that means. During a powerful earthquake, the Rion-Antirion bridge doesn't resist the shaking. It lets the shaking happen. The deck slides sideways. The shock absorbers convert the kinetic energy to heat, and the structure survives intact. After the earthquake passes, the fuses are replaced, the shock absorbers are reset, and the bridge is back to full service. This system was put to a real-world test on June 8, 2008, when an earthquake measuring 6.5 on the Richter scale struck southern Greece.
The bridge's monitoring system, which includes over 400 sensors tracking movement in real time, recorded the event. The fuses broke as designed. The shock absorbers engaged. The deck moved. And when the shaking stopped, the bridge was undamaged. The engineers called it a genuine life-size test of whether the project was well-founded. It was. The bridge survived one of the strongest earthquakes to hit the region in years, doing exactly what its designers intended. Not fighting the earthquake, but dancing with it. And the bridge was designed to handle even worse. The design basis earthquake for the Rion-Antirion Bridge is a 7.0 on the Richter scale, which would be a catastrophic event by any measure. During such an earthquake, the bridge deck can move laterally by over 11 feet relative to the pylons. The shock absorbers and fuse system are designed to accommodate this without any damage to the primary structure. After the earthquake, the replaceable components, the fuses, and the absorber fluid are serviced, and the bridge returns to full operation. There's also a detail about the bridge's relationship with the ground that borders on the philosophical. The Rion-Antirion Bridge doesn't fight the Earth. It acknowledges the Earth's power and designs around it. The footings aren't anchored because anchoring them would transfer the earthquake's energy into the bridge. The deck isn't fixed to the pylons because fixing it would concentrate stress at the connections. Everything about the design says, the Earth is going to move, and we're going to let it move. And we're going to survive by being flexible rather than strong. It's a profound shift from the Roman approach, where bridges were built to last forever by being massive and immovable. The Pont de Gare stands because it's too heavy and too solid to be pushed around. The Rion-Antirion Bridge stands for the opposite reason. It lasts because it moves, because it yields, because it absorbs and dissipates energy instead of fighting it head-on. In a way, the Rion-Antirion Bridge represents the most sophisticated answer yet to our central question. Where does the weight go? In an earthquake, the weight doesn't just go down, it goes sideways, violently. And the bridge has to accommodate that lateral force without breaking. The answer at Rion-Antirion is that the force goes into the shock absorbers, where it's converted to heat and dissipated harmlessly. The force is not resisted, it's consumed, transformed from destructive kinetic energy into benign thermal energy. And then, when the shaking stops, the bridge is still standing, ready for the next challenge. The engineers understood that sometimes the best answer to overwhelming force isn't more force. It's accommodation. The Rion-Antirion Bridge opened in 2004, and it's widely regarded as one of the most technically challenging bridges ever built. It solved problems that had no precedent, using solutions that had never been tried. And it did it in a place where the Earth itself is actively trying to pull the ground apart. Where does the weight go in the Rion-Antirion Bridge? Down through the deck, into the cable stays, through the pylons, into the massive footings, through the gravel bed, into the reinforced seabed, and into the clay far below. But the weight path is designed to be interruptible. In an earthquake, the connections between the deck and the pylons can break, allowing the deck to float independently for a few terrifying seconds, absorbing the shaking, before everything reconnects and the force path is restored. A bridge that can intentionally break and then heal itself.
That's 21st century engineering. Now, let me take you to one more bridge. Because no discussion of modern bridge engineering is complete without the Millau Viaduct, a structure so visually striking that the President of France, upon seeing it for the first time, got out of his car and simply said, "That was fantastic." The Millau Viaduct is in southern France, in the Tarn River Gorge, one of the deepest valleys in Europe. The town of Millau had been plagued for decades by terrible traffic jams. The highway from Paris to the Mediterranean coast ran right through the town, and every summer, hundreds of thousands of vacationers would get stuck in bumper-to-bumper traffic for hours. The solution was to reroute the highway across the gorge, bypassing Millau entirely. But the gorge is over 1.5 miles wide and over 900 feet deep. Bridging it would require a structure of unprecedented scale. The engineer who took on the challenge was Michel Virlogeux, a graduate of France's prestigious École Polytechnique, who had worked on nearly 200 bridges during his career. Virlogeux was already famous for designing the Pont de Normandie, a cable-stayed bridge with a record-breaking main span. At Millau, he faced something far more complex. The initial design studies explored several possible routes across the gorge. Most of them followed the valley walls, descending to a lower elevation before crossing. But then a road construction expert made a simple observation that changed everything. He asked, "Why don't you stay up at the same level as the plateaus?" Virlogeux later recalled thinking, "We were stupid. That's what we have to do." Instead of descending into the valley and climbing back out, the bridge would stay at plateau level, crossing the gorge at its highest point. It was a bold decision. It meant building the tallest bridge pylons in the world, but it would create a shorter, more elegant structure. And it would keep traffic moving at highway speed, rather than crawling down and up a steep slope. The design that emerged was a cable-stayed bridge with 7 pylons, the tallest reaching over 800 feet above the valley floor, taller than the Eiffel Tower. The bridge deck stretches just over 8,000 feet, and it sits about 900 feet above the bottom of the gorge. Each pylon splits into 2 slender shafts near the top, a distinctive Y shape that wasn't chosen for aesthetics, though the effect is visually stunning. The split design allows the deck to expand and contract with temperature changes. On a hot day, the steel deck can grow several feet longer than on a cold day, and the flexible split pylons can accommodate this movement without cracking. The bridge was designed in collaboration with British architect Norman Foster, and the two spent nearly a decade perfecting the plans before construction began in 2001. The construction itself was extraordinary. The steel deck, weighing about 36,000 tons, was assembled in workshops on the plateaus at either end of the bridge and then pushed into position using a system that exists nowhere else in the world. The deck was too heavy, and the pylons too tall and too flexible for conventional methods. So the engineers invented what they called wedge conveyors. Each conveyor consisted of 2 wedge-shaped blocks that slid over each other using hydraulic jacks. The first wedge would slide under the deck, lifting it slightly, about 3/4 of an inch. The second wedge, now free of the deck's weight, would advance forward by about 2 feet. Then the cycle would repeat. The deck crept forward, 2 feet at a time, pushed along by the rhythmic sliding of the wedges. This process took 15 months. The north and south sections of the deck inched toward each other, growing from either side of the gorge, balanced on the pylons like enormous seesaws. In May 2004, they met in the middle. To raise the 7 pylons, the engineers used a lifting system inspired by a technique that's been around for 4,000 years. The ancient Egyptians raised their obelisks at Luxor using a combination of ramps, levers, and counterweights.
The Miao engineers adapted this principle, developing custom lifting equipment that hoisted the pylon sections into place one by one. As one of the engineers put it, constructors must know all the techniques used for at least the past 4,000 years, whether they're Egyptian, Roman, 19th century, or 20th century. When you mix all that together, you can build great works of civil engineering that will be part of the long history of human construction. The construction of the pylons was itself a remarkable feat. All 7 pylons were built simultaneously to save time, each one growing about 13 feet every 3 days. The concrete was poured continuously, the molds climbing upward as the pylons rose. At the base of each pylon, the concrete is over 16 feet thick, and the footprint is the size of a tennis court. Below each pylon, 4 massive drilled shafts extend about 60 feet into the bedrock, anchoring the entire structure.
The pylons split into 2 slender shafts for the top 300 feet or so, giving them that distinctive forked appearance. The split isn't just elegant, it's functionally essential. The bridge deck, made of steel, expands and contracts with temperature. On a hot summer day, the deck can be several inches longer than on a frigid winter night. If the pylons were rigid single columns, this expansion and contraction would create enormous internal stresses. But the forked design allows the pylon legs to flex slightly, absorbing the deck's movement without cracking. The bridge breathes with the seasons, and the pylons flex with it. 150 workers, assisted by robotic welding equipment, assembled the steel deck sections in workshops on the plateaus at either end. More than 600 miles of welding were needed to join the steel plates together. The sections were pushed outward over the pylons using the wedge conveyors, balanced like an enormous seesaw, each side growing at the same rate to keep the forces even. It was, by several accounts, the most nerve-wracking phase of construction. The deck sections, weighing thousands of tons, crept forward at a pace of about 2 feet per cycle, balanced on pylons that were themselves flexible and swaying slightly in the wind. On a windy day, the top of the tallest pylon can move several inches from its resting position. During construction, before the cable stays were installed to stiffen the system, the movement was even greater. Workers on the advancing deck reported that the feeling was somewhat unsettling. Standing on a steel platform 800 feet in the air, feeling it sway gently, watching the pylons flex. The Miao Viaduct opened on December 14, 2004, after just 3 years of construction by a workforce of about 600 people. It still holds the record for the tallest pylon in the world. And it solved Miao's traffic problem completely. The highway now glides across the gorge at speed, and the old road through town sits mostly quiet. Galileo, who has designed some of the most significant cable-stayed bridges in the world, including the 3rd Bosphorus Bridge in Istanbul, which holds the record for the longest cable-stayed span at just under 5,000 feet, has reflected on the future of bridge engineering. He believes traditional materials, concrete and steel, will eventually reach their limits. Spans of perhaps 6,000 or 7,000 feet may be the maximum for cable-stayed construction. Beyond that, new materials will be needed, perhaps carbon fiber composites, perhaps something not yet invented. But whatever materials the future brings, Verlager insists the fundamental principles will remain the same. The principles that a Roman architect named Vitruvius articulated 2,000 years ago. Utilitas, firmitas, venustas. Usefulness, strength, and beauty. A bridge must serve a purpose. It must stand, and it must be worth looking at. Usefulness, strength, and beauty. Those three words have governed bridge design since the first stone arch was placed across a stream, and they still govern it today, in the age of cable-stayed megastructures and earthquake-dancing pylons and decks that float nearly a quarter mile above the ground. And beauty matters more than you might think. When communities are consulted about new bridge projects, aesthetics consistently ranks as one of their top concerns. People have to look at these structures every day. They have to drive across them. They have to live near them. A bridge that works perfectly but looks terrible is a failure, not of engineering, but of design. And conversely, a bridge that looks beautiful creates a sense of civic pride that goes far beyond its transportation function. The Golden Gate Bridge is the perfect example. It works beautifully as a bridge, but it also works as a symbol. You can show a picture of the Golden Gate Bridge to someone on the other side of the world, and they'll know it's San Francisco. The bridge is the city, and that identification, that sense of place and pride, came from decisions about color and proportion and lighting that were made by an architect, Irving Morrow, who never got nearly enough credit for his contribution. The Millau Viaduct is the same way. It didn't have to be beautiful. It could have been a utilitarian concrete slab on heavy piers, functionally identical, probably cheaper to build. But Verlager and Foster spent years refining the proportions, the pylon shape, the cable arrangement, until the bridge achieved something that transcends engineering. It looks like it belongs in the landscape. It looks like the landscape grew it. The best bridges don't just carry traffic. They carry meaning. They tell the world something about the community that built them, about the engineers who designed them, about the era that produced them. And that meaning, which is entirely human and entirely subjective, is woven into the same steel and concrete that carries the force of gravity down to the bedrock. So, where does the weight go? We've traced the path through every type of bridge humans have ever built, and the answer, at its core, has never changed. Force travels through the structure, following whatever path the engineer has designed for it, until it reaches the earth. Compression in the arches, tension in the cables, bending in the beams, compression in the towers, friction in the foundations, and finally, absorption into the rock and soil that have been carrying the weight of everything on this planet since long before human beings showed up and started building things. A log across a stream sends force straight down into the banks, through the wood of the trunk, by bending. Top in compression, bottom in tension. A Roman arch sends force along its curve, stone squeezing against stone until it reaches the abutments, where the outward thrust pushes into the riverbanks. A steel truss sends force through a network of triangulated members, some in compression, some in tension, each one carrying its load in a straight line to the supports. A suspension bridge sends force up through the suspender ropes into the main cables, which carry it in tension over the towers, which carry it down in compression, while the horizontal pull of the cables is absorbed by the massive anchorages on either shore. And a cable-stayed bridge sends force along straight cables directly into the towers, where it's channeled down through the concrete, through the foundations, and into the ground. No anchorages, no lateral thrust, just straight down. 5 different designs, 5 different force paths, but one universal principle. Force has to go somewhere, and the engineer's job is to give it a safe and reliable way to get there. Now I want to circle back to something I said at the very beginning, because there's a detail I glossed over that turns out to be more interesting than it might seem. When a bridge engineer designs a bridge, they don't just calculate the weight of the traffic, they also calculate the weight of the bridge itself. And in many cases, the weight of the bridge is the harder problem. A bridge engineer named Gary Johnson, who's been designing bridges for over 25 years, once explained it in a way that stuck with me. He said that the dead load, the weight of the bridge structure itself, is the first thing you have to design for. And you have to design for it in stages, because as you build a bridge, it gets heavier. When you place a steel beam, it has to hold up just itself. Then you pour concrete on top of the beam for the road deck. And now the beam has to hold up itself, plus the wet concrete, which is heavier than cured concrete because of the water in it. The wet concrete is, in fact, one of the most critical loading conditions in bridge design. The beam often has to be stronger than it needs to be for the traffic, just so it can survive the moment when the wet concrete is poured on top of it. Then there's the question of live loads, the loads that change. Trucks, cars, pedestrians, all the things that come and go on a bridge. And this is where bridge design gets particularly interesting, because the engineer doesn't know exactly what will cross the bridge in the future. They can predict, they can estimate, but they can't be certain. To handle this uncertainty, bridge engineers build in safety factors. The dead load, the weight of the bridge itself, is multiplied by 1.25. So if the bridge weighs £1 million, the engineer designs it to carry £1,250,000 of dead load. That 25% margin accounts for small variations in material weight, construction tolerances, and the inevitable additions of utilities and guardrails that accumulate over a bridge's life. But the live load gets a much bigger safety factor. It's multiplied by 1.75. The engineer takes the expected truck weight and increases it by 75%. Why such a big margin? Because live load is unpredictable. A bridge designed for normal trucks might one day be asked to carry a military convoy or an overloaded construction vehicle. A bridge designed for normal traffic might one day see a traffic jam that fills every lane with bumper-to-bumper trucks. The 75% margin is the engineer's acknowledgement that the future is uncertain and the bridge needs to handle surprises. And there's a load factor that surprises most people when they first hear about it. Impact. When a truck crosses a bridge, it doesn't apply its weight gently and evenly. It bounces. Every bump in the road surface causes the truck to jump slightly and then land again. And each landing applies a momentary force that's greater than the truck's static weight. Bridge engineers account for this by adding a 33% impact factor to the live load. A 30-ton truck, bouncing on an imperfect road surface, hits the bridge deck with the equivalent of about 40 tons. And once the bridge is built, the forces don't stop. There are live loads, trucks and cars and pedestrians, which come and go. There's wind, which pushes sideways, There's the impact of vehicles bouncing on the road surface, which adds about 33% to the live load. And there's something that almost nobody outside of engineering thinks about: temperature. A steel bridge deck expands when it's hot and contracts when it's cold. On a very long bridge, this expansion and contraction can amount to several inches or even several feet over the length of the bridge. If the deck were rigidly fixed at both ends, the thermal expansion would create enormous internal forces that could buckle the steel or crack the concrete. That's why bridges have expansion joints. Those bumps you feel when you drive from the road surface onto a bridge, and again when you drive off the other end, those are expansion joints. They're gaps in the road surface that allow the bridge deck to grow and shrink with the seasons, without building up internal stress. Some expansion joints are simple, just a rubber seal stuffed into a gap. Others are elaborate mechanical devices with interlocking steel fingers that can accommodate a foot or more of movement. The Golden Gate Bridge has copper expansion joints that let the steel deck flex in wind, expand in heat, and shift in earthquakes. Without those joints, the bridge would crack itself apart within a few years. And there's one more force that acts on every bridge every day without anyone noticing: creep. Creep is the slow, gradual deflection of a structure under sustained load. If you've ever noticed that the shelves in an old bookcase sag in the middle, that's creep. The wood has been carrying the weight of the books for years, and it has slowly, imperceptibly deformed under the constant pressure. It happens to bridges too. Concrete beams especially will deflect downward over time under the weight of the road surface and the traffic. To account for this, bridge engineers build beams with a slight upward curve, a feature called camber. When the beam arrives at the construction site, it's not flat. It has a hump in the middle, a few inches higher than the ends. As the concrete deck is poured, the beam deflects downward under the weight, and the hump flattens out. Over the years, as creep continues, the beam deflects a little more, and the road surface eventually settles to its design elevation. But on old bridges, especially ones with long, repetitive spans, the creep can become noticeable. If you've ever driven along a coastal bridge and felt a gentle galloping motion, your car rising and falling every few hundred feet, that's creep. The beams have sagged over decades, and the road surface dips slightly at the center of each span. It's not dangerous. The bridge was designed for it. But it's a physical reminder that bridges are not static objects. They're alive in a sense. They move, they breathe, they age, and the people who keep them alive, the inspectors and painters and maintenance crews, they're doing work that most of us never see and never think about. Every bridge in the United States that's open to traffic is inspected at least every 24 months. Some bridges, those with fracture-critical members, elements whose failure would cause the whole bridge to collapse, are inspected every 12 months. And some, those in the worst condition or the most critical locations, are inspected every 6 months. When an engineer inspects a bridge, they look at everything: the deck surface for cracks and potholes, the beams for corrosion and section loss, the bearings for movement and wear, the piers for settlement and cracking, the foundations for scour, the erosion of soil around the base of a bridge pier by flowing water, which can undermine the foundation and cause the pier to tilt or settle. Scour is one of the leading causes of bridge failure in the United States. When water flows past a bridge pier, it speeds up, and the faster-moving water erodes the soil around the base of the pier. Over time, the pier can end up sitting on a pillar of soil that's narrower than the pier itself, like a mushroom standing on a thin stalk. If the scour gets bad enough, the pier can tip over. To prevent this, engineers use riprap, large chunks of rock placed around the base of a pier to armor the soil against erosion. You've probably seen riprap without knowing what it was. Piles of angular boulders arranged around the bases of bridge piers in rivers and streams. It looks decorative, but it's structural. It's the last line of defense between the flowing water and the foundation. I mentioned fracture-critical members a moment ago, and they deserve a word of explanation, because they represent one of the most important concepts in bridge safety. A fracture-critical member is a structural element that is in tension, made of steel, and non-redundant, meaning that if it fails, there's no other element to pick up the load. The entire bridge, or at least a major section of it, would collapse. The concept of fracture-critical design became important after the collapse of the Silver Bridge at Point Pleasant, West Virginia, on December 15, 1967. The Silver Bridge was an I-bar chain suspension bridge, and it collapsed during rush hour, killing 46 people. The investigation found that a single I-bar, a flat steel link in one of the chain cables, had developed a tiny crack from metal fatigue. The crack grew slowly over years, invisible to the naked eye, until one day it propagated through the entire bar. The bar snapped. The chain it was part of failed, and the bridge fell into the Ohio River. 46 people died because of a crack smaller than a quarter of an inch. Cars and trucks plunged into the Ohio River during the evening rush hour, just days before Christmas. The bridge, which had been inspected and deemed safe, had hidden a fatal flaw in a single component for years, perhaps decades, while normal traffic passed overhead. The disaster transformed how America thinks about bridge inspection. Before Point Pleasant, bridge inspections were informal and inconsistent. After Point Pleasant, Congress passed the Federal Highway Act of 1968, which established the National Bridge Inspection Standards. For the first time, every bridge on the public road system was required to be inspected on a regular schedule by qualified engineers, using standardized methods and reporting formats. Today, there are over 617,000 bridges in the United States, and every single one that's open to public traffic has an inspection file. The data is maintained in the National Bridge Inventory, a massive database that tracks the condition of every bridge in the country. And the inspection system works. When engineers find a bridge that's deteriorating, it gets flagged, posted with weight restrictions if needed, and scheduled for repair or replacement. The system isn't perfect. No system is. But it has prevented countless potential disasters in the decades since it was established. After the Silver Bridge disaster, the United States Federal Highway Administration mandated that all bridges with fracture-critical members receive special inspection attention. Engineers now focus specifically on these elements during inspections, using techniques like magnetic particle testing and ultrasonic testing to detect cracks that are invisible to the naked eye. And in new bridge designs, engineers try to avoid fracture-critical details wherever possible, adding redundancy so that no single element failure can bring down the structure. Where does the weight go in a fracture-critical analysis? It goes the same place it always goes, through the structure to the ground. But the engineer is asking a more pointed question. What happens if part of the path fails? Where does the force go then? Is there an alternate path? Or does the bridge fall down? Good bridge design provides alternate paths, redundancy, multiple beams instead of one, multiple cables instead of one, extra piers, extra connections, extra layers of defense, so that if one element fails, the others can absorb the load until repairs are made. The Swiss cheese model that safety researchers use for analyzing accidents in nuclear power and aviation applies just as well to bridges. Every layer of protection, design, materials, construction quality, inspection, maintenance, is a slice of Swiss cheese with holes in it. A bridge fails when the holes line up. When the design has a weakness, and the material has a defect, and the inspection misses it, and the maintenance is deferred, and the loading exceeds the design basis, all at the same time. The entire history of bridge engineering is the story of adding more slices, of filling more holes, of making sure that the path from the bridge deck to the bedrock has so many redundancies, so many backup routes, that force always has somewhere safe to go. So, here you are, lying in the dark, and I've been talking about bridges for a while now, tracing the journey that force takes from the road surface to the earth, from the truck crossing the bridge to the bedrock far below. And maybe some of it has been interesting. And maybe some of it has been complicated. And maybe some of it has already started to blur as you drift towards sleep. But before you go, let me give you one last thought. The idea that force has to go somewhere, that weight travels through a structure until it finds something solid enough to absorb it. That idea doesn't just apply to bridges. It applies to everything you've ever stood on, sat on, leaned against, or lain upon. Right now, in this moment, your body is resting on your mattress, and the weight of your body is traveling through the mattress, through the bed frame, through the floor, through the foundation, and into the earth. Every layer is doing what a bridge does. It's receiving force from above and sending it to something below. Your mattress is a beam. Your bed frame is a pier. Your floor is a deck. Your foundation is an abutment. And the earth, the deep, solid, patient earth, is the final destination. Your body itself is a bridge, in a sense. Your spine is a column, carrying the weight of your head and torso down to your pelvis. Your pelvis is a pier, distributing the load into your legs. Your legs are piles, driven into the ground when you stand. And the bones, the muscles, the tendons, the ligaments, they're all carrying force, routing it along paths that evolution designed over millions of years, keeping you upright, keeping you balanced, keeping you from collapsing into a heap. Even lying down, the forces are there. Your ribs are arches, curving around your chest, channeling the weight of your organs outward to the spine. Your vertebrae are a column of interlocking blocks, each one carrying the compression of the ones above. And your muscles, even the ones that feel relaxed right now, are maintaining a baseline level of tension, holding everything in place, keeping the architecture of your body intact. You are a structure, and like every structure, like every bridge, you are constantly answering the question, where does the weight go? For you, the answer is into the bed, into the floor, into the ground. Let it go there. Let the weight travel down through all those layers, all those supports, all those foundations,
and let the earth hold it for you. That's what the earth does. It holds everything. It's been doing it for 4.5 billion years. Every bridge we talked about tonight is doing exactly this. The log across the stream is sending its load into the banks. The Pont du Gard is sending its load through 2,000 years of stone arches into the bedrock of Provence. The Brooklyn Bridge is pulling on its cables and pushing on its towers and pressing its enormous anchorages into the rock of Manhattan and Brooklyn.
The Golden Gate is swaying gently in the fog, its cables humming with tension, its towers absorbing millions of pounds of compression, while 35 painters work through the night to keep the rust at bay. And the Bay Panjang Bridge, the highest bridge in the world, is floating over a canyon so deep you can barely see the bottom, held up by nothing but cables and towers, and the absolute certainty of engineers who understood deeply and precisely where the weight needed to go. They all found the answer, and the answer is always the same. Down, through the structure, into the earth. That's where force goes. That's where weight ends up. And that's why bridges stand. The engineers figured this out over 3,000 years, piece by piece, bridge by bridge. Sometimes through triumph, and sometimes through tragedy. They figured it out with rope and stone and iron and steel and concrete. They figured it out by watching bridges fall and then building better ones. They figured it out because people needed to get to the other side, and the gap was in the way, and somebody had to solve the problem. And the problem, in the end, was always the same. Force has to go somewhere. Find it a path. Make sure the path is strong. And the bridge will stand. It will stand in the morning. It will stand next week. It will stand next year. The engineers made sure of that. They calculated every load, every force, every stress. They added safety margins. They designed for earthquakes and wind and ice and flood. They built in redundancy so that if something fails, something else catches the load. They inspected and they painted and they repaired and they inspected again. And the bridges stand. So, you can let go of the weight you're carrying tonight. Whatever it is, let it travel down through the mattress, through the bed, through the floor, through all those layers between you and the solid ground. The earth has been holding weight since before bridges, before buildings, before people. It can hold yours. Let the ideas settle. Let the arches and cables and towers drift into the quiet part of your mind where things don't need to be understood all at once, where they can just be there, like a bridge in the distance, standing in the dark, doing its job. The path of force through a bridge is a long, winding journey, but it always ends in the same place. Somewhere solid, somewhere stable, somewhere that has been holding weight for a very long time and will keep holding it for a very long time to come. That's where you are right now. Held, supported, resting on something solid. You don't need to think about any of this anymore. The bridges are out there, standing in the dark, answering the question they were designed to answer. Where does the weight go? Into the earth, every time. So let your breathing slow.